Hello there and welcome to Physics with William. I'm very glad you're here. Settle in, get comfortable, and let your mind loosen its grip on the day for a little while. Tonight we're going to spend some time with a question that sounds simple, almost childish at first, and then becomes much stranger the longer you look at it. Why can you not walk through a wall? It is one of those facts of life so familiar that most of us stop noticing it somewhere around early childhood. Floors hold us up. Chairs remain chairs. Tables do not allow our elbows to pass through them, however clumsy the morning may be. Walls are especially committed to being walls. They do not negotiate. You cannot reason with them. You cannot explain that you are in a hurry. You cannot tell them that from your point of view, this whole issue would be much more convenient if they simply relaxed for a moment and let you through. And yet, if you look at the story physics tells about matter, this ordinary stubbornness starts to seem a little surprising. Atoms are tiny. The things inside atoms are even tinier. Most of an atom is not a little hard marble-packed solid from edge to edge. Most of it is space. So why does your hand stop at the table? Why does your shoulder lose every argument with a door frame? Why does the world feel solid when the ingredients of matter are in some sense, mostly not there in the way we usually imagine? That is where tonight's subject enters the room quietly, like a rule that has been doing essential work for a very long time without demanding applause. It is called the Pauli Exclusion principle, and although the name sounds like something that lives in a difficult textbook and never goes outside, it is one of the reasons you have a body with shape, a bed that holds you, walls that remain respectfully external to your internal organs, and a world that does not collapse into a very disappointing smear. Before we get into that, let me ask you something I always enjoy wondering about. Where are you listening from tonight? Is it late where you are? Are you under a blanket, on a sofa, half paying attention while a cup of tea cools somewhere nearby? Are you in a city apartment with traffic still murmuring outside, or somewhere quiet enough that the house itself seems to be breathing? I like the thought that these ideas travel into all kinds of rooms and routines, arriving while someone is getting ready for sleep, folding laundry, staring at the ceiling, or pretending they are definitely about to go to bed in just a minute. And if you find this kind of slow physics comforting or useful, or just a pleasant way to let your brain wander somewhere interesting without needing to solve anything urgent, do consider liking the video and subscribing to the channel. It helps more people find these gentle little expeditions into the structure of reality, and it gives this very civilized arrangement of one person talking about quantum mechanics in a calm voice to another person probably lying down somewhere a fighting chance of continuing. Now, the usual answer to why you cannot walk through a wall sounds almost too obvious to be worth saying. Because the wall is solid, and so are you. End of story. Case closed. Please return to your regularly scheduled furniture. But that answer only works because it repeats the mystery in different words. Saying the wall is solid does not explain what solidity is. It just gives the phenomenon a label and hopes no one asks follow-up questions. Physics, unfortunately for our sleep but fortunately for our curiosity, is built out of follow-up questions. What does it mean for matter to be solid? What is actually happening when your hand presses against a tabletop? Why does the table push back? Why does one collection of atoms not simply slide through another collection of atoms as if they were loose crowds passing each other in a train station? Somewhere beneath the ordinary fact that things feel firm is a set of rules governing the smallest building blocks of matter, and those rules are not at all what common sense would guess. If you could shrink yourself down, far past cells and molecules and atoms, you would not find tiny billiard balls packed tightly together like oranges in a crate. That image is comforting, but it is wrong in all the important ways. Matter at small scales is not a neat little pile of miniature pebbles. It is a quantum system, and the behaviour of its ingredients is ruled by principles that do not care very much about our human expectations. One of the strangest facts you meet down there is that particles of the same kind can be deeply identical. Not just similar, not cousins, not members of the same brand, but identical in a way that ordinary objects in daily life never are. One electron is like another electron completely, with no secret scratch or private dent or slightly different shade of electron blue. Nature does not issue them serial personalities, it issues them as exact copies. That turns out to matter a great deal, because the universe has rules about what identical particles are allowed to do. Some particles are quite sociable, they're perfectly happy piling into the same state together. Others are much less accommodating. Electrons belong to the second group. They have a built-in refusal to share certain arrangements. Very roughly speaking, if one electron is already occupying a particular quantum state in an atom, another electron cannot simply step into that exact same role and declare that they will be twins now. The seat is taken. No duplicates allowed. This is the Pauli Exclusion principle in spirit, and while there is a more careful way to say it, that basic idea is enough for the moment. It is a rule about refusal, a rule about non-overlap at the level of allowed states, a rule that sounds modest until you realise that much of the visible world is built from the consequences of that refusal. To get a feel for how odd this is, it helps to notice how often our ordinary language sneaks in misleading pictures. We speak as if objects touch each other. We say your hand touches the wall, the mug touches the table, your feet touch the floor. It feels direct, simple, almost intimate. But from the point of view of microscopic physics, that word touch is doing a lot of work and not explaining much. What we call touch is not little chunks of matter peacefully interlocking like puzzle pieces finally finding their match. It is not your atoms settling into the gaps between the wall's atoms until everything is neatly combined. Quite the opposite. What you experience as contact is in large part the result of atoms strongly resisting that sort of overlap. The closer the outer electrons of one object are pushed toward the outer electrons of another, the more the quantum rules begin to object. And quantum rules do not raise their voice. They simply make the arrangement energetically unfavourable in a very firm and very effective way. This is one of those moments where reality becomes both less intuitive and more interesting. The wall feels hard not because matter is a little lumps of ancient stubborn stone packed all the way down, but because the electrons in the atoms making up your body and the electrons in the atoms making up the wall are governed by rules that prevent them from all collapsing into the same set of states. There are electromagnetic effects involved as well, and we will take our time with those, because the story is not a one-principle fairy tale, where a single sentence explains everything forever. Physics is rarely that tidy. Still, the exclusion principle is one of the central reasons matter has size and structure. It helps explain why atoms build layers instead of collapsing inward, why chemistry has variety instead of monotony, why materials have shapes, and why everyday objects maintain the deeply reassuring habit of not letting each other pass through on a whim. It is worth pausing here to appreciate how wonderfully rude the universe can be. At the human level, we spend a great deal of effort learning to share. Share toys, share snacks, share opinions with slightly less volume at family dinners. But electrons took another path. They looked at the concept of sharing identical quantum states and rejected it completely. Not unkindly, perhaps, but decisively. No, says the electron, that place is occupied. Find another. And because nature listens to this rule with perfect seriousness, electrons in atoms arrange themselves into shells and levels, instead of all settling into the same lowest option. If they could all pile into the lowest state together, atoms would be radically different. Chemistry as we know it would not exist. The periodic table would not be the periodic table. Carbon would not behave like carbon. Oxygen would not behave like oxygen. You would not behave like you. The ordinary richness of matter depends on particles refusing to become one bland crowd. That alone would make the principle important. But there is also something charming about how this hidden rule shapes our immediate physical world in such practical ways. It is the sort of deep quantum fact that eventually cashes out as, and this is why your elbow stops at the armrest. It is why your mattress supports you instead of letting you drift gently through it, like a disappointed ghost. It is why stones stack, why books rest on shelves, why buildings stay arranged in the order architects intended rather than passing through one another and settling into the basement in a mood of collective confusion. Behind these familiar acts of support and resistance lies not a universe made of miniature cannonballs, but one structured by rules about what quantum states identical particles may occupy. The funny thing is that for most of human history, nobody had any reason to suspect this. If you tap a wall, what you learn is that the wall remains unimpressed. That is useful information, but it does not immediately suggest a story about identical fermions and antisymmetric wave functions. And that is probably just as well, because it would have made carpentry unbearable. Human beings learned to live with solidity long before they understood any of it. We built homes, made pottery, stubbed toes, invented helmets, and developed an extensive body of practical knowledge about which surfaces are safest to run into and which are not. Science came later, asking not just how to cope with solid things, but what makes them solid in the first place. That turn from habit to explanation is one of the great pleasures of physics. It takes an everyday fact that has gone nearly invisible through familiarity and places it under a bright light until it becomes strange again. So let us make it strange in a careful, friendly way. Imagine pressing your hand against a wall. At first it feels as though your skin simply meets the wall and stops. Nothing could be more straightforward, but zoom in and the picture changes. The atoms in your hand are surrounded by electrons. The atoms in the wall are surrounded by electrons. As the distance between them decreases, those electron clouds begin to interact. They are charged, and charge matters. But along with the electromagnetic repulsion, there is also the deeper quantum bookkeeping of what arrangements are permitted. The electrons cannot all occupy the same states. That refusal contributes to a rapidly increasing resistance as matter is pushed closer together. In everyday life, this manifests as the ordinary sensation of solidity. It feels like contact. It feels like pressure. It feels like the wall saying no. And the wall is saying no in a language that was never designed for our comfort. It is speaking in terms of quantum states, energy levels, statistical behavior, and the identity of fermions. Which is, admittedly, not how most of us phrase our objections when someone leans on us in a queue. But the result is reliable enough to build civilizations on. You do not need to understand the Pauli Exclusion principle for it to protect your ankles from sinking through the stairs. Nature handles the paperwork. The universe is full of invisible regulations, and most of them are enforced without appeal. There is another layer to this that makes the story especially satisfying. The exclusion principle is not a bolt-on rule added to matter as a kind of safety feature. It is not there because the universe realized solid objects would be convenient for making cupboards. It comes out of the deeper structure of quantum theory and the kind of particles electrons are. In other words, the world is not solid because someone wanted tables. Tables exist because the underlying rules of quantum matter allow stable structures to emerge. That order of explanation matters. It reminds us that the familiar world is not basic. The familiar world is what deeper rules look like from the scale of sleepy mammals trying to carry mugs around without dropping them. This is often the direction physics moves. It takes us from the visible to the invisible, from the obvious to the underlying, from the practical fact to the hidden pattern that makes the fact possible. A wall is ordinary. The reason a wall is impenetrable is not ordinary at all. It is quantum mechanical. It involves a principle discovered in the early 20th century by Wolfgang Pauli, a physicist with a sharp mind, and by many accounts, a personality not especially softened by a desire to spare weaker ideas. Pauli helped identify a rule that at first seemed aimed at the behavior of electrons in atoms, but whose consequences spread outward into chemistry, materials, astronomy, and your very immediate inability to stroll through your house like mist. That spread from microscopic rule to everyday reality is what makes this topic so satisfying. Some ideas in physics are grand in a distant way. They tell you about black holes, early cosmology, or the edges of the observable universe. Those are wonderful subjects, but they can feel far from the life of a person listening in bed. The Pauli exclusion principle is different. It is deeply strange, deeply fundamental, and also personally relevant every second of your life. It is involved in the firmness of the pillow under your head, the shape of your hands, the stability of your bones, the behavior of the air, the architecture of atoms, and the reason walking through walls remains stubbornly absent from your skill set. Of course, whenever a rule sounds this important, it is natural to wonder whether it explains everything by itself. Not quite. Physics usually prefers teamwork. The solid feel of matter involves electromagnetic interactions as well as quantum exclusion. The full account is richer than any one sentence, but exclusion is one of the indispensable parts. Remove it, and the structure of matter changes so radically that familiar reality goes with it. Keep it, and atoms stack their electrons in ordered ways, chemistry blooms into variety, and objects acquire size instead of collapsing into far smaller states. The world gains room. Not empty room in the ordinary sense, but structured room. The kind of room that lets matter resist matter. That phrase may sound slightly severe, but resistance is not always a bad thing. In fact, it is one of the quiet kindnesses of the physical world. Because matter resists being compressed into the same states, you can lie down on a bed instead of falling through it. Because atoms have structure, there are surfaces to lean on, roofs that stay up, cups that hold soup, and bones that can do the thankless work of carrying around a thoughtful ape who occasionally forgets where he left his keys. The universe is not only energetic and dynamic, it is supportive, in a very literal sense because its smallest ingredients obey certain restrictions. When you hear the phrase exclusion principle, it might sound like a negative statement, a rule about what cannot happen, and it is that, but physics is full of fruitful cannots. You cannot exceed certain limits. You cannot make matter ignore all its own constraints. You cannot pack identical fermions into the same quantum state without consequences. These restrictions are not merely prohibitions, they are the framework out of which stable patterns emerge. Much of the world we value depends less on freedom than on form. Not every arrangement is allowed, and because of that, atoms become distinct, materials become diverse, and the universe avoids becoming a featureless soup. So tonight we begin with the wall. Not because walls are glamorous, though they are very dependable, but because they give us a way into one of quantum physics' most important ideas through an experience no one needs explained. Everyone knows what it is like to be stopped by the world. A hand against a door, a foot against the floor, a forehead against the consequences of not turning the kitchen light on. These small collisions are the everyday face of a deeper order. The world appears solid because matter is not free to arrange itself arbitrarily. Electrons have rules. Atoms have structure, objects have boundaries, and once you start seeing that, the ordinary room around you begins to look less like a collection of passive things, and more like an ongoing negotiation conducted by the quantum properties of matter. In a moment, we can slow down further and look at this solidity itself, because it is one thing to say that the world feels solid and another to examine what that feeling really amounts to. Why everyday objects seem so full and substantial, even though their atoms are mostly not what common sense expects, and why the first step toward understanding why you cannot walk through walls is to realize just how strange it is that anything feels solid at all. That's a strange place to begin, with the suggestion that what feels most obvious about the world may be one of the least obvious things about it. Solidity seems like the kind of fact no one should need help with. You wake up in a room full of solid things. The bed beneath you is solid. The floor waiting for your feet is solid. The door, the cup, the window frame, the spoon in the kitchen drawer, the book on the table itself, all of them seem to belong to the same dependable category. They are there. They have shape. They do not allow casual trespass. If you put your hand out sooner or later, something stops it. That is what the world feels like from the scale of ordinary life. It feels substantial. It feels packed. It feels filled in. It feels, in the most straightforward possible sense, real. And yet the more carefully you sit with that feeling, the more curious it becomes. Solidity is not just a property of rocks and walls. It is one of the basic ways reality introduces itself to you. Long before anyone learns the language of atoms or electrons or quantum mechanics, they learn firmness, A child learns it by knocking a toy against the floor, by bumping into the corner of a table, by discovering that the family dog is softer than the kitchen cabinet but not, unfortunately, as patient. Even the difference between safe and unsafe, comfortable and uncomfortable, possible and impossible, is deeply tied to whether matter yields or resists. We navigate by the pushback of things. We trust surfaces. We judge distance by when something becomes touch. We spend nearly every waking moment in a conversation with solidity so constant that we stop hearing it. That is part of what makes it such a good subject for slow thinking. The most familiar features of existence are often the ones we examine least. Ask a person what gravity is, and they may hesitate, but they know at once what it feels like. Ask what time is, and the room becomes philosophical very quickly. Ask why objects are solid, and you usually get some version of the question repeated back to you. They are solid because they are made of matter, and matter is the stuff that is solid. It sounds reasonable right up until you notice that it explains nothing. It is like answering why bread is bread by saying that it has all the important breadness. Pleasant for the bread, perhaps, but not very illuminating, so it helps to return to your own experience and notice what solidity actually consists of. Not in theory yet, just in feeling. Press your hand gently against whatever is nearest. A blanket will give way. A mattress will yield more. A wooden desk will hardly yield at all. Metal feels harder than wood. Stone feels firmer than fabric. Water accepts your hand and then surrounds it. Air allows almost complete passage, though not entirely, as anyone cycling into a strong wind can confirm with some bitterness. These differences are so obvious that we treat them as simple, but they are not simple. They are rich with information about how matter is arranged and how it responds to being disturbed. One way to notice this is to think about how many different kinds of solidity the world contains. A pillow is solid enough to support your head, but not solid enough to stop your finger from sinking into it. A ceramic mug resists your grip in a very different way. A sheet of paper bends, folds, and tears. A wall remains steady unless you bring either a hammer or a regrettable level of determination. Ice is solid in a way liquid water is not, yet both are made of the same basic molecules. Bread has structure, but not the sort you would use to build a bridge. A human body is astonishingly solid in some ways and remarkably delicate in others. Bones hold shape, skin stretches, muscle pushes back, lungs fill and empty. Teeth remain convincingly mineral until they meet the wrong caramel. The more you look, the less solidity appears to be one single thing. It starts to look like a family of related behaviours, all tied to how matter arranges itself and resists intrusion. That is where everyday life becomes a very quiet laboratory. Sit in a chair and you feel support. Lean against a wall and you feel resistance. Place a book on a table and it does not drift downward through the wood. Drop a spoon and the floor interrupts its ambitions. Stack plates in a cupboard and each plate accepts the weight of the ones above it, without dissolving into porcelain sadness. None of this feels mysterious when you are loading a dishwasher. It only becomes mysterious when you stop using these events as background and start asking what is actually happening. What does it mean for the chair to support you? What is the table doing when it holds the book up? Why does the floor know, with such flawless consistency, how to disagree with a falling object? The first temptation is to imagine ordinary contact as a kind of meeting between little pieces. Your hand reaches the table, the little bits in your hand meet the little bits in the table, and there is nowhere further to go because matter is full all the way through. That picture is extremely intuitive and deeply misleading. It borrows its confidence from the scale of human perception. At our size, surfaces appear continuous. Wood looks like a surface. Steel looks like a surface. Skin looks like a surface. We do not see the restless activity underneath. We do not experience the tiny distances and structures that make these materials what they are. We simply meet the result and call it solidity. There is also something psychologically comforting about solid things. They promise reliability. the world could have been much stranger at the scale of daily life. We might have lived in a universe where ordinary objects shimmered in and out of place, or where the firmness of a staircase changed with the weather, or where cups occasionally lost interest in containing liquids. Instead, we live among surfaces that are wonderfully predictable. Chair's chair, floor's floor, wall's wall. Even when materials differ, their behaviour remains ordered enough for bodies like ours to survive. This regularity is easy to take for granted, but it is not trivial. The stability of ordinary matter is one of the great background achievements of the universe. You and I do not usually wake up astonished that the house is still taking shape in the same arrangement it had yesterday. We should perhaps be a little more impressed. Part of that impression comes from noticing how much trust we place in solidity without conscious thought. Every step you take is an act of confidence that the ground will refuse you exactly enough. When you set down a glass, you trust the table to say no to it at precisely the right height. When you lie down to sleep, you assume the mattress will meet you, rather than shrugging politely and letting you continue downward toward the structural mysteries of the building. Life would be exhausting if we had to renegotiate all of this from scratch every morning, but because matter behaves with such astonishing consistency, we can save our anxiety for the more advanced hazards of existence, such as emails, tax forms, and the sound a laptop makes when it slides a little too close to the edge of a desk. Still, solidity is not absolute. That's another reason it deserves a closer look. Everyday objects resist in degrees. Push against a sponge and it compresses. Push against a spring and it deforms, then rebounds. Push against soft clay and it keeps the record of your impatience. Even the hardest materials bend slightly under enough force. A steel bridge flexes, a stone can crack. A diamond, for all its reputation, has its own vulnerabilities. Solids are not magical blocks of pure refusal. They are systems whose internal structure determines how they respond to pressure, strain, heat, and motion. Some hold their form rigidly, some flow slowly under stress, some shatter, some bounce back. Some store energy as they are bent and then release it suddenly, to the surprise of the person who assumed the ruler was no longer emotionally invested in the situation. So when we ask why you cannot walk through a wall, we're not asking only about walls, we're asking what makes matter occupy space in a stable way. We're asking why things have boundaries at all. Why does your hand end where it ends? Why does a chair maintain its outline? Why does a loaf of bread not seep sideways into a featureless mound the moment it is left alone? Why does one material welcome pressure while another resist it? The answers begin in the microscopic organization of matter, but before we go there it is worth staying with the human scale for a little longer, because the experience itself contains clues. Consider the sensation of touch. It feels direct. You place your fingers on a tabletop, and you would naturally say that you're touching the table. But what is that sensation exactly? Not philosophically in the grand sense, but physically. Your skin deforms. Tiny receptors in it respond to pressure, texture, vibration, temperature. Nerves carry signals. Your brain assembles them into a coherent event called touching wood, or touching glass, or touching fabric. Already there is more interpretation involved than daily language admits. Touch is not a simple announcement from reality. It is a constructed experience based on how your body responds to interactions at its surface. What feels like a plain meeting between you and the world is a translation. That translation is so good that it hides its own complexity. You do not feel atoms, you do not feel electrons, you do not feel quantum states objecting to one another. You feel smoothness, roughness, warmth, pressure, softness, hardness. Those are very real experiences, but they are the large-scale summary, not the microscopic story. It is a little like hearing an orchestra from outside the concert hall and saying the building sounds rich. That is true in a sense, but what you're hearing is the blended result of many distinct contributions. Solidity is like that. It is a surface fact produced by deeper patterns. This becomes especially vivid when you compare materials that are built from similar ingredients yet behave very differently. Graphite and diamond are both forms of carbon, and yet one crumbles onto paper as pencil marks, while the other is famous for extraordinary hardness. Wood can be carved, glass can be shattered, rubber bends and returns, wax yields under a thumbnail. These are not random moods of matter. They reflect how atoms are arranged, how strongly they bind, how the resulting structures distribute force, and how willing they are to change shape when pressured. So even before we reach quantum mechanics, everyday solidity is already telling us that matter is an organized thing, not just a heap. It also tells us that emptiness and resistance are not opposites in the way they seem. At the level of daily intuition, we imagine that what resists must be packed, dense, full through and through. If something contains space, surely that should make it easier to pass through. That sounds sensible until physics starts describing what atoms are actually like. Then the old intuition begins to wobble, because matter can be mostly space in one sense, and still be profoundly resistant in another. A building can have many rooms and still be impossible to walk through if you are approaching it from the wrong angle and at the wrong scale. That is only an analogy, of course, but it points toward the coming surprise. The world is not solid because it is stuffed without gaps like a badly packed suitcase. It is solid because of how its constituents are arranged and what rules govern their interaction. There is something almost comic about this mismatch between appearance and underlying explanation. From the outside, a brick wall looks like the most straightforward thing imaginable. It has the confidence of a fact that does not need defending. No one gazes at a brick wall and thinks, there must be a deep quantum story here. Yet there is. There always is. The world is full of objects that look complete at human scale and become astonishingly strange when questioned. A spoon becomes atoms. Atoms become nuclei and electrons. Electrons obey principles that care nothing for the common sense developed by creatures who mostly needed to avoid falling out of trees and later became overconfident enough to invent cutlery. It is also useful to notice that solidity is not only about stopping motion, it is about allowing form to persist. A mountain remains a mountain because the rock composing it resists casual rearrangement. A chair remains chair-shaped because its materials do not simply run away from each other. Your body maintains structure because its molecules are engaged in a ceaseless, organized dance that preserves larger patterns long enough for you to have a biography. Even something soft and yielding like a sweater has enough solidity to count as a thing. It keeps a loose shape. It occupies space. It pushes back a little when handled. So solidity is not the same as hardness. Hardness is one expression of it. Solidity in the broader sense is more like the general fact that matter forms stable arrangements with boundaries and mechanical behavior. The ordinary world gives us endless demonstrations of this. Think of cooking. Butter softens, flour dusts, dough resists and stretches. Sugar granules crunch, vegetables snap or wilt depending on what has happened to their internal structures. Think of weather. Ice hardens a puddle into a brittle surface. Heat softens tar until it becomes sticky underfoot. Think of furniture. A sofa cushion slowly adapts to years of sitting, while the frame hidden inside keeps doing the stern and uncelebrated work of not folding in half. Think of books, curtains, shoes, spoons, carpets, windows, bread crusts, apples, pillows, and doorknobs. The material world is not a single note. It is an entire range of ways matter can be solid, and beneath all those differences sits the deeper puzzle. What is it, in the end, that makes matter behave like this at all? Why does the world not behave like a ghostly overlap of barely connected bits? Why do objects have such strong opinions about where other objects are allowed to be? Why does the simple act of placing one thing on another work so beautifully? The answer will lead us into the architecture of atoms, into the strange status of electrons, into the reason identical particles do not behave like polite guests who are happy to bunch together wherever space seems available. But it helps to arrive there by first letting the ordinary fact of solidity regain its strangeness. Because once you really see it, the everyday world becomes slightly uncanny in a very healthy way. Not frightening, just more alive to explanation. The mug in your hand is no longer merely a mug. It is a stable arrangement of matter, structured by hidden rules. The chair beneath you is not merely a chair. It is a successful negotiation between gravity, atomic bonding, mechanical design, and the refusal of matter to permit certain kinds of overlap. Your own body is not a simple block of stuff, but a layered, dynamic material system that somehow feels unified from the inside. Even the quiet pressure of clothing against skin becomes evidence that the universe is busy enforcing order at scales too small to see. This is one of the pleasures of physics when approached slowly. It does not take the magic out of the world. It changes the kind of magic. It replaces the dullness of over-familiarity with the fascination of understanding. A wall does not become less interesting once you know it is not simply a hard slab in the naive sense. It becomes more interesting. It becomes a visible consequence of invisible constraints. It becomes a lesson in how the deepest laws of nature show up as the most ordinary features of your day. It becomes the answer to a question you did not know you had been living inside. So the curious solidity of everyday things is not merely that they are firm. It is that their firmness seems obvious only because you're used to it. Underneath that habit lies a profound and delicate arrangement. Matter occupies space. Matter resists compression. Matter forms surfaces, structures, and bodies. Matter gives you a room to be in and a world to move through. But the reasons it does so are stranger than they look from the scale of hands and tables. To see that properly, we have to take the next step and ask what sort of thing an atom really is. Because once you begin to look closely at the material world, the first unsettling discovery is that what seems most packed and substantial is not packed in the way you've probably imagined at all. By this point, the picture has become a little uncomfortable in the best way. We have spent so much of life trusting solidity that it feels almost rude to discover how strange it really is. Now the strangeness deepens, because when physics began to look closely at the atom, it found something that seemed to cut directly against the ordinary feeling of the world. Matter does not appear to be packed tightly from edge to edge. In a very important sense, it is mostly empty. And yet, that emptiness does not help you walk through a wall, slide your hand through a table, or sink quietly through the floorboards in the night like a puzzled Victorian ghost. The world remains stubbornly impassable. So now we have two facts that do not seem eager to coexist. Matter is largely empty, and matter is also very good at refusing passage. That sounds contradictory only because the word empty does a bit of mischief here. In ordinary life, when we say something is empty, we mean that there is room to move through it. An empty hallway can be crossed. An empty cup can be filled. An empty room does not stop you unless you have managed to trip over the emptiness itself, which would be a separate problem and perhaps a sign that bedtime has been postponed too long. But the emptiness inside atoms is not empty in the ordinary household sense. It does not mean there are neat little corridors between the pieces, waiting politely for you to stroll through. It means the structure of matter is not what common sense once imagined. The mass is concentrated in a tiny nucleus. The electrons are not little pebbles circling like planets in a childishly tidy orbit. The size of the atom is set by a broader quantum arrangement. Between the tiny nucleus and the region defined by those electrons, there is not solid material in the old billiard ball sense, and yet the atom remains very much a thing. This was one of the great shocks of modern physics. For a long time, people had imagined matter as if it were built from miniature hard grains. Not unreasonable, really. If sand is made of grains and flour of finer grains, perhaps everything is made of smaller and smaller little lumps until at last you reach the final tiny solid pieces. That picture has a certain practical charm. It is easy to imagine. It is easy to trust. It makes the world feel like a stack of little stones. But atoms turned out not to be like that. Once scientists learned to probe matter more carefully, they found that an atom has a tiny nucleus at its centre and a surrounding quantum structure that gives the atom its extent. The nucleus is astonishingly small compared with the full size of the atom. If you tried to picture an atom as a cathedral, the nucleus would not be a stone at the centre the size of the altar. It would be much smaller, more like a speck, while the atom as a whole would stretch out enormously beyond it. That comparison is crude, but it helps with scale. The important point is that the atom is not full in the way a brick looks full. If you enlarged an atom to the size of a large building, the nucleus would still be tiny. Most of the atom would not be a packed interior. It would be structured emptiness, if we can borrow that phrase without letting it become too vague. There is organisation there, not vacancy in the simple sense. The atom has shape, influence, boundaries of a kind. It is not a cloud in the meteorological sense, and not a marble either. It is a quantum object, which means our ordinary categories are already beginning to wobble. At first glance, this discovery seems to invite a practical question. If atoms are mostly empty space, why can objects made of atoms not pass through one another? Why does your hand not simply thread its way through the apparent gaps in the wall? Why does a chair not allow you to sink through it atom by atom? Why do the atoms in your body not slip between the atoms in the floor? It is a good question, and it becomes even better when you realise how naturally the mind wants to imagine this, like a problem of fitting small things through holes. If there are gaps, perhaps there should be room. If matter is sparse, perhaps solidity should be an illusion we could overcome with sufficient patience or optimism. But the atom is not a tiny solar system, with little empty roads between orbiting particles. That old picture survives because it is easy to draw, not because it is truly faithful to what atoms are like. Electrons are not miniature planets tracing precise paths around a nuclear sun. Quantum mechanics replaced that picture with something more subtle and harder to make intuitive. Electrons exist in states that are spread out, described by probabilities and constraints rather than classical little tracks. The atom is a region structured by these states, so the apparent emptiness is not a set of clean channels. It is not like a wire fence at microscopic scale where, with enough luck, one object might pass between the bars. Matter is organised by fields, charges and quantum rules, not by little billiard balls leaving navigable streets between them. This is one of the moments where language tries to betray us. We say there is empty space in the atom, and our minds immediately supply the wrong kind of emptiness. We imagine the inside of an atom as a room with furniture pushed far apart. It is not like that. The atom is not a mostly vacant apartment with one very tiny tenant at the centre, and a few restless guests wandering the perimeter. It is a bound system. Its structure is maintained by electromagnetic attraction between the positively charged nucleus and the negatively charged electrons, and the behaviour of those electrons is governed by quantum mechanics. So even before we arrive at the exclusion principle itself, we already need to let go of the idea that microscopic emptiness ought to make passage simple. There is another reason the old intuition fails. To pass through a wall is not merely a matter of finding a route through a few individual atoms. Your body is itself made of atoms, and those atoms come with their own electron structures, their own electromagnetic influence, their own quantum restrictions. The wall is not a static grid waiting to be infiltrated by a single point. It is a huge collection of atoms with their electrons arranged in matter that is already occupying a stable configuration. Your body is another such collection. When they approach each other, the relevant question is not whether one set of nuclei can slip between the other set of nuclei as though navigating traffic. The question is what happens when the full quantum structures of two organised collections of matter begin to overlap. That is where the apparent emptiness stops being helpful. Imagine trying to push two crowds through each other in a narrow station, except every person in both crowds carries an invisible rulebook about where they are allowed to stand and how closely they may duplicate one another. Even that is too simple, but it begins to hint at the issue. Matter is not just arranged in space. Matter occupies allowed states, and those states are not free to merge arbitrarily. So when your hand meets a wall, the problem is not that your atoms have failed to locate the holes. The problem is that the electrons in the atoms of your hand and the electrons in the atoms of the wall are now interacting in ways governed by charge and by quantum exclusion. The energy cost of forcing those structures into the same arrangement rises very quickly. What you feel as solidity is the large-scale result of that resistance. It is worth slowing down over the phrase energy cost because it sounds technical in a way that can blur the meaning. In ordinary terms, if matter can be arranged in one way easily and another way only with enormous difficulty, the first arrangement will dominate daily life. Nature is not sentimental. It prefers what is allowed and stable. Pushing two objects into each other in such a way that their electrons would have to occupy forbidden or highly unfavourable arrangements is not something the world casually grants. Instead, the objects push back. They resist. A force emerges from the underlying interactions, and your hand stops. You interpret that stopping as contact with a solid surface. The surface feels simple. The underlying reason is not. There is something deeply satisfying about that once you get used to it. The wall is not hard because it is packed with continuous substance all the way through like some ancient philosophical ideal of material stubbornness. It is hard because atoms are stable quantum systems, and because collections of atoms resist being forced into overlapping states. In other words, the wall is solid not in spite of atomic emptiness, but because emptiness was never the main issue. Structure was. Rules were. The architecture of matter matters more than our old picture of little filled-in lumps. This also helps explain why matter can be both mostly empty and surprisingly strong. Consider the skeleton of a bridge, or the frame of the building. Much of the volume in a building is empty air, and yet the structure can hold tremendous weight, because of how the material is arranged, and how forces are distributed through it. That analogy has limits, of course, but it reminds us that emptiness does not automatically mean weakness. A thing can contain a great deal of room and still possess strong form. At the atomic scale, the situation is much stranger, but the same lesson applies. What matters is not mere fullness. What matters is the relation between the parts and the rules they obey. The discovery that atoms are mostly empty also forced a change in how humans thought about touch. Earlier, touch could be imagined as tiny solid particles making direct contact like pebbles pressing together. The modern view is subtler. When two objects seem to touch, what is really happening is that the electron structures of their atoms are interacting strongly enough to prevent further easy approach. There is no need for tiny surfaces to scrape against each other in the old mechanical way. What matters is the interaction between charged quantum systems. Your fingertip does not tunnel into the table because the conditions for such overlap are overwhelmingly unfavourable. Instead, the table exerts an upward resistance, and your nerves report firmness. That word tunnel deserves caution here, because it belongs to a real quantum phenomenon that sometimes tempts people into strange hopes. Quantum tunnelling does allow particles to appear on the other side of barriers, in circumstances where classical physics would forbid it. But that does not mean your entire body is on the verge of phasing through a bedroom wall if only everyone in the room believes hard enough. The probability for a large object made of an immense number of particles to tunnel through a wall as a whole is so fantastically tiny that you can safely continue using doors. Physics is many things, but on this point it remains reassuringly conservative. There is another subtlety worth noticing. When we say matter is mostly empty, we are often talking about spatial distribution relative to the tiny nucleus. But the atom is not just a nucleus sitting in vacancy. The electrons define a region of influence and probability. They are what makes atoms interact at the scales relevant to chemistry, bonding, and the properties of materials. So the atom has extent because of electron behaviour. It is not emptiness surrounded by a vague halo for decorative effect. The so-called empty region is exactly where the quantum story is doing crucial work. That is why calling it empty without explanation can mislead. It is not empty in the sense of being physically irrelevant. It is where the atom lives as an atom, and once many atoms gather into matter, their electron structures begin to determine everything from chemical bonding to elasticity, to conductivity to hardness. Wood behaves differently from glass because the arrangements and bonds differ. Metal conducts and bends in characteristic ways because of how its electrons are organised. Rubber stretches because its molecular structure responds differently under stress. Bone is strong and slightly flexible because of its composite architecture. The world of material properties is, in large part, the world of atoms and electrons making collective arrangements. So when you press on a wall, you're not confronting a pile of tiny nuclei with gaps between them. You're confronting a material whose atomic and electronic structure has combined into macroscopic resistance. This is one reason why the phrase mostly empty can be both true and not very useful unless it is handled carefully. It is true in the sense that atomic mass is highly concentrated and atoms are not continuous miniature blocks. But if the phrase leads you to picture matter as easy to pass through, it has failed to educate and merely entertained. The real lesson is stranger and better. Matter is not solid because it is full. Matter is solid because the particles and fields composing it are arranged in stable ways that strongly resist certain kinds of overlap. That sounds less dramatic than saying atoms are mostly empty, but it is the more important idea. There is also a humbling quality to this whole subject. Human intuition evolved for the middle world of fruit, stone, rain, trees, skin, footsteps, and the occasional regrettable encounter with furniture in the dark. It did not evolve to understand atoms, so it is hardly a scandal that our first guesses are wrong. What would be more surprising is if the true structure of matter turned out to match exactly the instincts of creatures who spent most of their history trying not to be eaten, and only recently began building particle accelerators. The success of physics lies partly in its willingness to distrust what feels obvious when nature begins to reveal a deeper arrangement. And the deeper arrangement here is wonderfully clear once it settles in. Atoms are not miniature cannonballs, they are quantum systems. Their nuclei are tiny. Their extent is set by electrons. Collections of atoms form materials whose electron structures and bonds determine their behaviour. When two such collections approach, they do not simply interpenetrate because there are no neat passageways to exploit, and because the relevant electron configurations strongly resist overlap. So the emptiness inside atoms is real, but it is not the sort of emptiness that grants passage. It is the emptiness of a structured quantum world, not the emptiness of an abandoned hallway. This turns the ordinary room around you into something richer. The wall beside you is not an obstacle because it is built from featureless chunks. It is an obstacle because the atoms composing it are organised in a way that excludes and repels intrusion at the scale of your body. The bed beneath you supports you not because it is completely packed, but because its material structure can bear load through these same underlying interactions. Your own body, meanwhile, is equally structured and equally unable to ignore the quantum rules governing matter. Two organised systems meet, and the result is support, pressure, resistance, and the ongoing failure of human beings to pass dramatically through their own furniture. At this stage, one feature of the story is beginning to stand out above the rest. The world does not merely refuse overlap because of some vague mechanical inconvenience. There is a very specific rule hiding underneath the behaviour of electrons, a rule that says identical particles of a certain kind cannot all settle into the same quantum state. That rule turns out to be one of the quiet foundations of atomic structure, chemistry, and the everyday solidity of matter. It is not the whole story, but it is one of its essential sentences, and once that sentence was first written down clearly by Wolfgang Pauli, the strange fact that matter is mostly empty and yet never passable began to make a great deal more sense. The story becomes much clearer once a particular person walks into it, because physics often feels less remote when it is attached to an actual human mind trying to solve an actual problem. In this case, the person was Wolfgang Pauli, and the problem was not, at least on the surface, why you cannot walk through walls. Nobody in the early 20th century was gathered around a laboratory table saying, "Gentlemen, the wall situation remains unacceptable." The immediate puzzle was more technical and more specific. Physicists were trying to understand atoms. They were trying to understand why electrons arranged themselves the way they did, why the periodic table had the structure it had, why certain patterns appeared in the atomic spectra, and why older models of the atom seemed to work just well enough to be tempting, and then fail just badly enough to be irritating. This was a lively period in physics, though lively in the way physics often is, which means a great deal of quiet concentration, blackboards covered with increasingly urgent thought, and very bright people becoming deeply annoyed that nature refused to behave according to their preferred diagrams. The atom had already stopped being the simple indivisible unit once imagined by earlier thinkers. It had gained internal structure. There was a nucleus. There were electrons. There were signs that those electrons did not behave like tiny classical particles in neat little orbits that could be described with the calm confidence of planetary motion. The old pictures were beginning to crack. Something deeper was going on. Pauli arrived in that atmosphere with a reputation for extraordinary intelligence and an unusually low tolerance for nonsense. He was one of those people whose approval you probably wanted and whose disapproval you definitely did not want. There is a long tradition in science of sharp minds delivering sharp remarks, and Pauli was very much part of that tradition. He was not famous for padding criticism with emotional cushioning. If an idea was bad, he was prepared to say so. This may not always have been enjoyable for the person on the receiving end, but it did mean that Pauli was not easily impressed by weak explanations. He wanted the rules beneath the appearances. He wanted the world to make sense properly. By the 1920s, one stubborn problem involved the arrangement of electrons in atoms. The periodic table was there, chemistry was there, the regular pattern of elements was there for everyone to see, but the underlying reason for that pattern was not fully understood. Why did atoms not simply cram all their electrons into the lowest available arrangement around the nucleus? If they were attracted to the positive charge of the nucleus, why did they not all settle as close in as possible and remain there? Why did atoms have layered structure? Why did different elements behave differently? Why did chemistry have this varied and orderly richness instead of collapsing into something much simpler and much less useful? This is where Pauli made one of the great moves in modern physics. He realized that electrons must be subject to a restriction that had not yet been clearly stated in the right form. In simple terms, no two electrons in the same atom could occupy exactly the same quantum state. That sentence sounds modest. It does not have the drama of a thunderstorm or a launch countdown. It does not sound like a statement that ought to reorganize our understanding of matter. And yet it did. It was one of those rules that appears at first like an item of bureaucratic housekeeping, and then turns out to be holding half the building up. To appreciate why this mattered, it helps to get a feel for what a quantum state means in this context. We are not talking about a little coloured seat with a number on it, though that analogy can be useful if handled carefully. In an atom, an electron is described by a set of properties that determine its allowed behaviour. It is not enough to say that an electron is near the nucleus or far from it. Quantum theory tells us that only certain arrangements are allowed, and each allowed arrangement can be distinguished by a collection of characteristics. If one electron is already in a state with a particular full set of those characteristics, another electron cannot duplicate it exactly within the same atom. The second electron must differ in some way. It must take another allowed state. That restriction was the exclusion principle. It was not a suggestion. It was not a matter of electrons being shy, moody, territorial, or especially fond of personal space in the social sense. It was a structural rule built into the kind of particles electrons are, and once that rule is in place, the architecture of atoms begins to make sense. Electrons cannot all pile into the very lowest arrangement. They fill available states in an ordered way. Shells emerge, layers emerge, chemical behaviour emerges. The periodic table stops looking like a mysterious chart that chemistry keeps around for emotional reasons and starts to look like the visible record of a deep, quantum rule. This is one of those moments in science where a hidden sentence suddenly explains a large amount of visible reality. Before the rule is known, the world presents a pile of facts. After the rule is known, the facts begin to line up. that does not mean everything becomes easy overnight. Quantum mechanics was not exactly a field known for offering restful simplicity. But Pauli had identified something foundational. The exclusion principle explained why electrons in atoms organize themselves rather than collapsing into sameness. It showed why matter has internal differentiation. And because the behavior of atoms determines the behavior of chemistry, the consequences spread outward very quickly. There is something almost funny about how much the world owes to particles refusing to duplicate one another. Human beings build societies through all sorts of positive ideals: cooperation, conversation, trade, empathy, law, compromise, and the occasional passive-aggressive note left in a shared kitchen. Electrons build the material basis of the world by enforcing a strict rule of non-identity in their allowed states. No, says the universe at this level, not all of you in the same place in the same way. Spread out, organize yourselves, become structure, and from that refusal comes the shape of atoms, the variety of elements, the possibility of molecules, the existence of materials, and eventually the very normal experience of a person trying unsuccessfully to walk through a wall. It is worth emphasizing that Pauli did not invent the world into behaving this way. He recognized and stated the rule. That distinction matters because physics is not legislation. It is discovery. Pauli did not announce a policy and wait for electrons to comply. He identified a regularity that nature had been obeying all along. The brilliance lies in seeing the necessity of the rule before its consequences are fully mapped. That is often what great physicists do. They notice the hidden condition required for many puzzling facts to make sense at once. Pauli himself was not working in isolation from the rest of quantum theory. The 1920s were full of rapid changes in how physicists understood matter. Old ideas were being revised at extraordinary speed. New mathematical frameworks were appearing. Arguments were frequent. Confidence was unstable. Some things that had seemed obvious turned out to be wrong. Some things that had seemed absurd turned out to be correct. The atmosphere must have been both exhilarating and exhausting, which is probably true of any field going through a conceptual earthquake. Pauli was one of the central figures in that moment, and the exclusion principle became one of the indispensable tools for understanding the new atomic world. Now, there is a deeper layer to the story that later physics clarified even further. Electrons belong to a class of particles now called fermions. Fermions obey the exclusion principle. They are fundamentally different in this respect from another class of particles called bosons, which are perfectly willing to share states in ways fermions are not. That distinction turned out to reach far beyond atomic structure. But even without going deeply into the later formalism, the practical message remains the same. Electrons are not free to stack into identical arrangements. They must occupy distinct states. That is why atoms have size and organization. That is why the chemical character of elements depends on how their electrons are arranged. That is why matter does not all collapse into a simpler and much less interesting condition. When you hear this for the first time, it can sound almost too clean. Surely there must be more to it than that. And there is. Real physical explanations are usually layered. Electromagnetic attraction binds electrons to nuclei. Quantum mechanics defines the allowed states. The exclusion principle restricts how electrons fill those states. Together these produce the structure of atoms. But the exclusion principle is one of the key constraints without which the rest of the story changes radically. Remove it, and you do not get the periodic table we know. You do not get ordinary chemistry. You do not get carbon behaving as carbon and oxygen behaving as oxygen. You do not get the stable diversity of matter that makes biology, geology, furniture, bread, and astronomy all possible in their familiar forms. This is part of what makes Pauli such a satisfying figure in the story. He's not merely a name attached to an equation in a textbook. He is the person associated with a rule that reaches into daily life in a very direct way, even though its statement sounds abstract. Every solid object around you depends in part on the fact that electrons are subject to this restriction. The shape of your body depends on it. The The structure of your bones depends on it. The behaviour of the atoms in your skin, your bed, the wall and the floor depends on it. You're not aware of it in any ordinary sensory way. No one wakes up and says, yes, I can really feel the exclusion principle working for me today. But it is there, invisibly organising the possible. There is also a nice intellectual discipline in the way Pauli approached the problem. He did not settle for vague statements about electrons somehow finding a comfortable arrangement. Physics often begins in vague statements, but it cannot remain there. Comfort is not a physical law. Preference is not a mechanism. You need a rule that tells you what is allowed and what is forbidden. The exclusion principle does exactly that. It turns a fuzzy intuition into a definite constraint. No two electrons in the same atom can share the exact same quantum state. Once that is said clearly, the world becomes more legible. Think about what that means for a larger atom with many electrons. The first few electrons can occupy the lowest energy states available. But once those are filled, additional electrons cannot simply join them in identical arrangements. They must occupy higher or otherwise distinct states. That forces electrons outward into shells and subshells. It gives atoms extension. It creates patterns in the outer electrons of different elements, and those outer electrons are exactly what drive chemical behaviour. The whole visible drama of chemistry depends on the microscopic seating arrangement, if we may borrow that loose image for a moment, and the seating arrangement depends on the exclusion principle. Without it, atoms would not possess the same layered individuality. Matter would be profoundly different. The world would lose its structural richness. This is not one of those cases where a scientific principle only matters in a laboratory. It matters in the kitchen, in the bloodstream, in the mountain range, in the teacup, in the winter coat, in the hinge of the door, and in the impossibility of passing through the door without opening it first. The exclusion principle is one of those quiet laws that become almost comically important once you see what depends on them. Pauli himself later became associated not only with deep theoretical work, but also with a kind of scientific folklore. There was a famous joke among physicists about the Pauli effect, the supposed tendency of experimental equipment to fail whenever Pauli came near it. This was not a formal principle of nature, though one imagines it might have been emotionally true for certain laboratories. It is a charming detail because it rounds out the picture of him as something more than a stern monument. He was a formidable thinker, but also a real person moving through a real scientific culture, surrounded by admiration, fear, jokes, arguments, and the normal chaos that follows brilliant humans wherever they gather. Still, his most lasting contribution to our present discussion is this rule of exclusion. It tells us that the electron world has boundaries built into it. Those boundaries are not visible as fences or walls at the atomic scale. They are restrictions on allowed states, and those restrictions scale upward into physical consequences. Matter takes up room because electrons are arranged in structured ways that cannot all collapse into one state. Matter resists compression because forcing electrons into closer overlap runs into quantum restrictions. Matter achieves stability because its constituents are not free to pile into the same lowest arrangement. From these microscopic facts comes the large-scale experience of solidity. This is also where the title of our whole subject starts to feel less metaphorical and more literal. Why can you not walk through walls? Because the atoms in your body and the atoms in the wall are not composed of little inert pellets that might happen to slip through a lattice if aligned carefully enough. They are made of electrons and nuclei organised by quantum laws. As the electron structures of your body and the wall are pushed toward overlap, electromagnetic effects matter, and the exclusion principle matters. The world refuses the arrangement. Your body is told, in the calm but absolute language of physics, that this particular overlap is not on the menu, and that refusal is not an emergency response. It is normal operation. Every time you sit down, every time you lean on a table, every time your feet meet the ground, you are depending on the exclusion principle doing its work inside the atoms of ordinary matter. The universe is quietly enforcing Pauli's rule on a scale so small that no eye can witness it directly, yet the result is as immediate as the pressure of a chair beneath you. That is one of the pleasures of foundational physics. It shows how a principle discovered in the struggle to understand atomic spectra turns out to be part of the reason you're not currently halfway through the sofa. For now, the main thing to hold on to is the character of the rule itself. It is a rule of limitation, but not a sterile one. It is limitation that produces form. Electrons cannot all be the same in the same place in the same way, so atoms become structured. Structured atoms become chemically distinct. Distinct chemistry becomes the diversity of matter. Diverse matter becomes the physical world you know. A prohibition at the bottom becomes abundance at the top. That is a very common pattern in nature, though it rarely presents itself with such clarity. So Pauli's insight was not just another technical footnote in the development of quantum theory, it was a statement about what kind of world is possible. A world with exclusion is a world with stable atoms, varied elements, persistent structures and solid matter. A world without it would not look remotely like home, and once that begins to settle in, the next thing to ask is how this rule, which first appears in the behaviour of electrons inside atoms, scales outward into the familiar fact that matter takes up space at all, because that is where the ordinary room around you starts to look like the direct consequence of quantum particles refusing to be arranged any old way. To see how this quiet rule turns into the visible structure of matter, it helps to linger with a simple image for a moment, not because the image is perfectly accurate, but because it gives the mind something gentle to hold while the real idea settles in. Imagine that an atom contains a set of allowed places for electrons, not places in the ordinary sense of tiny chairs arranged in tidy circles, but allowed roles, allowed arrangements, allowed ways of being part of the atom. People often reach for the language of seats because it captures the most important feature. Some states are available, some fill up. Once a state is occupied in the right way, another electron cannot simply sit in the very same one and pretend the universe will not notice. The universe notices. It notices with total consistency and absolutely no flexibility. That does not mean electrons are little people, queuing politely around the nucleus with numbered tickets. Quantum mechanics is never quite that friendly. But the seat image works for one crucial reason. It reminds us that not everything is allowed. An atom is not a place where electrons may arrange themselves however they please. There is a limited set of possible states, each defined by quantum rules, and electrons fill those states in an orderly fashion. Once you understand that, the atom stops looking like a vague little cloud of charge and starts looking like a built structure. Not built by hands, of course, and not built from intention, but built from rules. The architecture of matter begins there. The phrase shell is part of that architecture. It is one of those scientific words that entered popular language because it is useful, even if it can become a little too visual if taken too literally. When we talk about electron shells, we are referring to broad groupings of allowed states in atoms. These are levels of organization. Electrons closer to the nucleus generally occupy lower energy arrangements. Additional electrons cannot all squeeze into those same lowest arrangements, so they begin to fill higher groupings. This layering gives atoms internal order. It means atoms are not just nuclei with a random haze of electrons around them. They have pattern, they have arrangement, they have something like a floor plan. This is where the exclusion principle becomes much more than a curious restriction. It becomes an organizing force. Suppose there were no such rule. Then electrons attracted to the positive nucleus would be free to keep settling into the same lower state without limit. The atom would not build outward in the same way. It would not acquire the same layered structure. The difference between one element and another would lose the form we know. Chemistry would change beyond recognition. So when we say that electrons fill shells, what we are really saying is that matter has no choice but to become structured. The exclusion principle refuses collapse into sameness, and in doing so, it compels order. That order is one of the hidden reasons the periodic table makes sense. At first, the periodic table can look like a chart someone designed, because they were very committed to neat rows and did not want to waste a good rectangle. But beneath the rows and columns is a logic tied to how electrons occupy states. Elements differ by the number of protons in the nucleus, yes, but the chemical personality of an element depends heavily on the arrangement of its electrons, especially those in the outermost regions. As electrons fill shells and related structures within those shells, patterns repeat. Elements with similar outer electron arrangements tend to behave in similar ways. The periodic table is not just a filing system for atoms, it is a map of quantum architecture. That architecture is what allows matter to have variety without chaos. Hydrogen behaves one way, helium another, carbon another still. Oxygen has its own habits. Sodium is not remotely the same sort of conversationalist as neon. Iron has one kind of role to play in the world, chlorine another. The richness of chemistry comes from these differences, and the differences come from how electrons are arranged under quantum rules. It is one of the great achievements of physics that something as practical and observable as chemical behavior can be traced back to the occupancy rules of invisible particles. What feels at first like an abstract rule about electrons becomes, by the time it reaches daily life, the reason bread bakes, lungs function, oceans exist, and batteries do what they do. There is a calm beauty to that. Matter is not improvised. Matter is disciplined. Not in a moral sense, obviously. An electron is not virtuous because it obeys quantum mechanics. It has no option in the matter, but the result still feels elegant. The atom is a structured entity because only certain arrangements are allowed. The shells are not decorations around the nucleus. They are the shape of possibility. They tell you how electrons may inhabit the atom. They tell you where repetition is permitted and where it is forbidden. And because electrons in the same atom cannot all be identical in their state, the atom gains depth and extension. This is one reason the seat analogy has to be used carefully. If you imagine a room with ordinary chairs, the room itself is already there, waiting passively, and the people simply enter and fill it. An atom is not quite like that. The allowed states are not chairs placed inside a pre-existing container. The states are part of what the atom is. The electron arrangements help define the atom's spatial extent, its stability, its ability to interact with other atoms. So the architecture is not merely interior design. It is constitutive. It is the very making of the structure. If the allowed states were different, the atom would be a different kind of thing altogether. And this is where the word shell can mislead in another way. It suggests a hard boundary, like the shell of an egg or the shell of a nut. Electron shells are nothing like that. They are not thin, rigid surfaces wrapped around the nucleus. They are ranges of allowed states with characteristic energies and distributions. Still, the old word survives because it conveys layering, and layering is indeed part of the truth. Atoms are layered not because someone stacked physical rings around a center, but because quantum rules produce families of allowed arrangements that fill in sequence. The world of matter depends on that sequence. Once you begin to picture atoms this way, many familiar facts become less mysterious. Why do atoms bond in some patterns and not others? Why do some elements react eagerly while others remain almost comically indifferent? Why are some materials brittle, others flexible, others conductive, others insulating? Why does life rely so heavily on a relatively small set of elements? Why does carbon, in particular, become the astonishingly versatile backbone of biological chemistry? Over and over, the answer leads back to electron arrangement. Not arrangement in the casual sense of where things happen to be floating today, but arrangement in the deep quantum sense of what states are available and how they are filled. Carbon is a wonderful example, not because it is uniquely magical, but because it shows how much follows from these rules. Carbon has an electron arrangement that makes it exceptionally good at forming stable and varied bonds. That is one of the reasons chemistry becomes rich enough for life. Carbon can form chains, rings, frameworks, large molecules with subtle shapes and functions. None of that happens because carbon woke up ambitious. It happens because its electron architecture, shaped by the allowed filling of states, gives it certain possibilities. The entire biological world rides on such possibilities. Trees, skin, proteins, sugars, nerves, hair, blood, memory, all of it ultimately depends on atoms whose electrons occupy quantum states according to rules Pauli helped make visible. This can sound almost too grand, so it helps to come back down to something closer to hand. Consider a simple object, a ceramic mug. It looks stable, ordinary, almost dull in its reliability. But the mug exists as a coherent object because its atoms are arranged into a material with strong bonds and a particular structure. Those bonds depend on electron behavior. Electron behavior depends on allowed states. Allowed states are filled according to quantum principles, including exclusion. So the mug on the table is a piece of large-scale evidence that electrons do not all collapse into one indistinguishable crowd. The mug is not merely clay that has been baked, it is quantum order made useful. You can say something similar about a table, a spoon, a fingernail, or a leaf. Every stable object is a sort of frozen history of allowed states and resulting bonds. Even things that feel soft or unstable are still structured in this sense. A blanket does not hold together by politeness. A loaf of bread does not maintain its crumb, because flour is sentimental. There are atoms, molecules, interactions, constraints. The world is intimate with quantum mechanics whether or not it speaks the language. That intimacy becomes especially visible when we think about the outer electrons of atoms. Inner electrons occupy lower energy states and are often tightly associated with the nucleus. Outer electrons are usually the ones most involved in bonding and chemical interaction. They are in a sense the social boundary of the atom, not social in the human way of course, but in the sense that they determine how one atom encounters another. Whether atoms bond strongly, weakly, not at all, or in very particular geometries depends largely on what is happening with these outer states. So the architecture within the atom becomes the architecture between atoms, and that becomes the architecture of materials. This is one of the most satisfying chains of explanation in all of science. A microscopic rule about identical particles leads to ordered electron filling. Ordered electron filling leads to atomic structure. Atomic structure leads to chemical behavior. Chemical behavior leads to molecules and materials. Molecules and materials lead to rocks, rivers, lungs, timber, brick, blood, raincoats, violin strings, coffee cups, sea salt, clouds of breath in winter air, and the ordinary impossibility of putting your hand through a wall. None of those steps is arbitrary. Each follows from the one before in a way that makes the universe feel at once more strange and more coherent. Now, there is an important difference between the neatness of the basic idea and the complexity of real atoms. Real atomic structure is not just a simple list of shells filled one after another with cartoon tidiness. Within shells there are subshells and further distinctions. The allowed states have different shapes and energies. The ordering can become subtle. In larger atoms, interactions among many electrons make the details richer and more complicated. But the broad principle remains. There are allowed states. They fill in constrained ways. Electrons cannot duplicate one another completely within the same system. The result is organized matter. That organization also helps explain why the world has texture instead of monotony. If all atoms behaved the same way, matter would be terribly dull. You would not have metals, ceramics, gases, liquids, proteins, sugars, or the astonishingly varied chemistry that living things depend on. You would not have colour in the same sense because colour depends on how matter interacts with light, and that interaction depends on electron structure. You would not have the same mechanical properties because stiffness, elasticity, brittleness, and conductivity all grow out of how atoms bond and how electrons behave collectively in materials. The exclusion principle, by forcing structured occupation of states, is part of the reason the world has character. It is also part of the reason matter takes up space in a durable way, because electrons cannot all occupy the same lowest arrangement, atoms have extent. They build outward. Their electron distributions define regions where interactions with other atoms become significant. This is essential for understanding why matter is not just a set of tiny nuclei rattling around in a void. The atom's size is not an afterthought. It is the result of quantum organization. And once atoms have size, structure, and differentiated outer behavior, they can form larger structures that are stable enough to build the visible world. If you zoom out from the scale of one atom to the scale of a crystal, a piece of metal, a wooden beam, or a strand of DNA, you begin to see how architecture repeats. Small-scale order becomes large-scale order. In a crystal, atoms may arrange in regular repeating patterns. In a protein, a chain of atoms folds into a shape with extraordinary functional importance. In metal, electrons can behave collectively in ways that allow conduction and characteristic mechanical strength. In each case, the story begins with the allowed states of electrons and the restrictions on how they may be occupied. Matter is architectural all the way down and all the way up. There are local arrangements and global consequences. Perhaps this is why the seat image remains so stubbornly useful. We know it is too simple, yet it expresses the essential fact that occupancy matters, order matters, availability matters. A filled arrangement is different from an unfilled one. A partly filled outer region behaves differently from a complete one. Chemistry changes because of these differences. The physical world changes with chemistry. So while electrons are not sitting in chairs around a nucleus like very serious guests at a formal dinner, there is still something helpful in remembering that the room of possibility is not infinite and the placements are not arbitrary. There is also a quiet comfort in the thought that the stability of the world is not accidental. It is not that matter usually behaves itself and we are lucky most days. It is that matter is built on rules strong enough to produce stable forms over and over. When you rest your hand on a table, you are touching the outcome of that stability. When you breathe, you're depending on the chemistry of molecules whose existence depends on electron structure. When you walk across a room, every step is supported by materials whose architecture traces back to these hidden arrangements. The universe is not improvising the floor beneath you every second. It has already done the deeper work. Of course, the architecture of matter is not static in the absolute sense. Atoms vibrate in solids. Molecules rotate, flex, react. Materials expand when heated, fracture under stress, change phase under new conditions. Chemistry is dynamic. Biology is restless. The world is full of motion. But underneath that motion is a stable grammar, the allowed states of electrons and the exclusion principle that helps govern their occupation provide part of that grammar. They do not tell the whole story, but without them the story would be unreadable. And this is why the subject never really stays confined to atoms in isolation. Once you understand shells and occupancy, you have already begun to explain the visible universe at human scale, why elements differ, why materials differ, why objects have persistence, why surfaces resist, why structures hold. The atom is not too small to matter. It is the scale at which matter first becomes itself. Everything larger inherits the consequences. So when we say quantum seats, shells, and the architecture of matter, what we are really talking about is the hidden plan that gives the world its ordinary reliability. Not a plan in the sense of intention, but in the sense of pattern. A world where electrons can only occupy certain states, and cannot all pile into the same one, is a world where atoms acquire structured layers. Structured layers produce chemical identity. Chemical identity produces the variety and solidity of things, and once that begins to settle in, the next question arrives almost on its own. If exclusion and electron arrangement give atom structure, then is this also the reason matter occupies space so stubbornly in the first place? Because that is where the architecture of the atom becomes the simple, everyday fact that a body cannot share the same room in the same way as the wall beside it. There is a question hiding underneath almost every object you have ever used, and it is easy to miss because the answer seems too obvious. Why does matter take up space at all? A stone takes up space. A chair takes up space. A loaf of bread, a sleeping cat, a glass of water, your own body in the bed or on the sofa right now, all of it occupies room in the world. If you put one object somewhere, another object cannot simply claim that exact same arrangement without trouble. There is an ordinary firmness to existence that makes this seem natural. Of course, matter takes up space. What else would it do? But once you begin asking deeper questions, that certainty starts to thin out. Why should matter have extent? Why should an atom not collapse into something vastly smaller? Why should a body have edges? Why should a solid object refuse to be compressed indefinitely into less and less room? Somewhere beneath all these familiar facts lies a deeper explanation, and it is one of the most important in all of physics. At first, it is tempting to answer in the old intuitive way. Matter takes up space because it is made of little bits, and little bits by definition need room. It sounds reasonable. If you pile pebbles into a box, they occupy volume. If you pack oranges into a crate, the crate fills. So perhaps atoms are just the smallest possible little chunks, each with its own tiny size, and ordinary objects take up space because they are collections of those tiny chunks stacked together. That picture is comforting. It has the neat simplicity of a cupboard arranged by someone who enjoys labels. The trouble is that it does not survive contact with the actual structure of atoms. Atoms are not tiny hard pellets in the simple mechanical sense. Their size is not the size of a miniature marble. Their extent comes from something much stranger. An atom has a tiny nucleus, and electrons arranged in quantum states around it. The nucleus carries most of the mass. The electrons help determine the size of the atom. That already tells us something important. The space an atom occupies is not mostly the result of a big, heavy center taking up room. The center is extremely small. What gives the atom its extent is the behavior of its electrons, and the behavior of electrons is governed by quantum rules. So when we ask why matter takes up space, we're really asking why electrons do not all collapse inward, why atoms acquire stable size, and why collections of atoms resist being squeezed into the same arrangements. This is where the exclusion principle begins to show its full practical power. Electrons cannot all occupy the same quantum state. That sentence may sound as though it belongs in a lecture hall and not in a bedroom or kitchen or hallway, but it has an immediate consequence. If electrons in an atom are not free to pile into one identical lowest arrangement, then the atom must build outward into a structured set of occupied states. In other words, the atom gets size because the electrons are forced into an organized distribution rather than a total collapse into sameness. The world of matter becomes spacious in a very literal sense because nature does not permit certain kinds of repetition. There is something quietly remarkable about that. The extent of matter is not a primitive fact. It is not that particles simply arrive with tiny little hard shells and declare that this much room is theirs. The room is created by the allowed structure of the quantum system. Atomic size is the outward form of invisible restrictions. What looks from a distance like simple occupancy is, underneath, a delicate consequence of what kinds of states are allowed and how they must be filled. You can see why this matters by imagining the alternative. Suppose electrons were free to ignore the exclusion principle. Suppose they could all drop into the same lowest state around the nucleus without limit. Then atoms would not have the same layered electron structure. They would be far smaller and far less differentiated. Chemistry would change beyond recognition. Matter would not present the same rich variety of forms and behaviors. The visible world would lose much of its architecture. It is hard to overstate how radical that difference would be. You would not merely lose a detail of textbook physics. You would lose the familiar scale and shape of material existence. But exclusion is not acting alone. This is important, because physics rarely permits a single sentence to do all the work. The size of atoms and the way matter occupies space arise from a partnership between quantum mechanics and electromagnetic interaction. Electrons are attracted to the positively charged nucleus. That attraction tends to bind them into the atom, but they are not free to simply collapse into the same arrangement, because quantum rules prevent identical electrons from sharing the exact same state. The result is a stable balance. Atoms are neither infinitely spread out nor collapsed into nothing. They acquire definite structure and extent. This helps explain why matter is not just somewhere, but somewhere in a stubborn way. An object is not merely present in space as a loose collection of points. It occupies a region through the organized distribution of its atoms, and those atoms themselves occupy space through their electron structure. So when you place a book on a table, the book is not a bag of tiny grains resting on another bag of tiny grains. It is a structured collection of atoms whose electron arrangements define a volume, and the table is another such structured collection. The reason the book does not continue downward is that these occupied structures resist being forced into greater overlap. The world has thickness because the underlying matter has extent. There is also a useful distinction here between simply being located somewhere and taking up space. A mathematical point can be located somewhere without having size. Matter is not like that. Matter does not merely mark a position. It excludes other matter from certain arrangements. It creates boundaries, not necessarily sharp in the simplistic sense, but real enough that objects have form and do not casually merge into one another. This is a profound feature of the universe. Matter is not ghostlike. It is not content to pass through itself without objection. It insists on arrangement. That insistence becomes clearer when you think about compression. If matter took up space in only a loose or accidental way, then perhaps objects could be squeezed arbitrarily smaller without much resistance, but real matter pushes back. Compress a cushion, and it yields some distance, then resists more strongly. Compress a metal rod, and it resists sooner and more firmly. Compress a gas, and its pressure rises. Compress matter enough under extreme conditions, and strange new states can appear, but the general lesson remains. Matter does not simply surrender all its volume. It resists being crowded. That resistance is one of the main reasons objects occupy space in a durable sense, rather than merely drifting in it. At the level of atoms, this resistance comes from how electrons are arranged and how they respond when forced closer together. If you try to squeeze matter, you're not pushing on empty philosophical substance. You're changing the quantum environment of many electrons at once. Some available states are already filled. Pushing atoms closer means forcing electrons into a situation where the allowed arrangements become more constrained and energetically less favorable. The system resists. Matter presses back. From a human perspective, this feels like firmness. From the microscopic perspective, it is quantum organization refusing to be casually rearranged. This is one of the reasons the phrase takes up space should not sound passive. Matter is not lounging in volume by coincidence. Matter actively maintains extent because of the rules governing its constituents. A body occupies space in the same way a melody occupies time, not as a static block but as an organized pattern that cannot simply be collapsed into a single instant without ceasing to be what it is. That analogy has limits, but it captures something essential. Matter is structured extension. Its size and form are consequences of order. If that begins to sound abstract, it helps to return to ordinary things. Think of a mattress. It supports you because its material structure gives underload in controlled ways, but not indefinitely. Think of a wooden table. It hardly seems to yield at all, yet on a smaller scale the atoms within it still respond to stress. Think of a ball of wool, a ceramic bowl, a block of ice, a sponge, a coin. All of them take up space differently. They resist compression differently. They hold shape with different levels of determination. But in each case, there is a common theme. The material consists of atoms arranged into a structure that occupies room and resists overlap according to the interactions and constraints at the atomic scale. It is also worth noticing that space occupancy is not just about resistance to outside intrusion. It is about internal coherence. Why does an object keep its own shape instead of collapsing inward? Why does your body not shrink to a tiny dense knot? Why does a crystal retain its lattice? Why does a drop of water have a certain volume at a given temperature and pressure? All of these depend on the balance of forces and quantum rules within matter itself. Matter takes up space not only because it keeps other matter out, but because its own internal arrangement stabilizes a certain extent. The atomic story is especially striking because what we call the size of an atom is largely determined by the region in which its outer electrons are distributed. That is the scale at which atoms interact with one another chemically and mechanically. So the size of matter is, in a deep sense, an electron story. The nucleus provides charge and mass, but the size is the outward quantum architecture built around it. This means that the everyday dimensions of objects are, indirectly, dimensions set by electron behavior. The width of a table leg, the thickness of a page, the curve of a fingernail, the size of a raindrop on glass, all of them trace back to matter whose atoms have size because electrons cannot all collapse into the same arrangement. There is a strange comfort in that once it settles in. The world is not bulky for crude reasons. It is bulky because the smallest ingredients obey rules that produce extension. Reality at our scale is spacious because reality at smaller scales is constrained. The universe gives us room by forbidding certain crowdings. It is a very elegant arrangement. A negative rule becomes a positive world. This also helps explain why material properties vary so much. Different kinds of matter take up space in different ways because the bonds between atoms differ, the arrangements of electrons differ, and the collective behavior of the material differs. In a gas, atoms or molecules are relatively far apart and free to move, so the material fills a container and can be compressed more easily. In a liquid, molecules are closer together and interact more strongly, so the material has a fairly definite volume but can still flow. In a solid, the atoms or molecules occupy a more fixed structure, so the material maintains shape and strongly resists shear and compression. These are different expressions of how matter occupies space. The same basic physical principles produce a whole family of behaviors. Solids are especially important for our subject because they give the most obvious example of space occupancy. A wall takes up space in a way that feels absolute. But even there, the deeper story is not one of featureless filling. It is one of stable atomic arrangement. A wall is a large-scale pattern of matter held together by bonds, supported by electron structure, and made resistant by the inability of its constituent particles to be forced into arbitrary overlap. The wall has thickness because the material has a stable form. That stable form is grounded in quantum rules. So when you stand in front of a wall, you're really standing in front of a vast organized population of atoms whose occupied states and mutual interactions create a macroscopic boundary. There is also a reason this subject reaches beyond everyday surfaces into more extreme parts of the universe. Under enormous pressure, matter can be compressed far more than in ordinary life, but not without limit. In dense stars, for example, the same basic principles become dramatically important. When gravity tries to crush matter inward, quantum rules fight back. Electrons resist being pushed into the same states. Under even more extreme conditions, other particles may take over the burden of resistance. The details belong to later in the story, but even now you can see the point. The reason matter takes up space is not just a domestic convenience for tables and chairs. It is a cosmic fact strong enough to help stars resist collapse. That may be one of the loveliest things about this principle. The same rule that helps explain why your body does not pass through a mattress also helps explain why certain stars do not collapse entirely under their own weight. Physics has this habit of connecting the intimate and the enormous. A law discovered while studying atomic behavior ends up helping support the furniture of the cosmos. It is almost unfairly elegant. Still, for our purposes, the immediate lesson is enough. Matter takes up space because atoms have size. Atoms have size because their electrons occupy structured quantum states, and those states cannot all be collapsed into identical arrangements. Once many atoms form materials, their organized structure creates stable objects with boundaries and resistance. This is why the world around you is not a blur of interpenetrating possibility. It is a world of chairs, walls, blankets, books, and bodies, each insisting on its own arrangement. And yet even that is not quite the end of the matter. Because once you say that matter takes up space through atomic structure and quantum exclusion, another question appears almost immediately. What does it actually mean in lived experience for one object to meet another? When your hand rests on the table, what is happening at the boundary between them? What is touch, really, if the world is built not from simple hard lumps but from charged quantum systems resisting overlap? That is where this story becomes even more intimate, because the next thing to understand is that what we call contact is not quite contact in the ordinary sense at all. That is where the story moves from the structure of matter into the structure of experience, because it is one thing to say that atoms occupy space and resist overlap, and another to ask what that resistance feels like from inside a human nervous system. We say that we touch things all the time. We touch a table. We touch a door handle. We touch the fabric of a blanket, the rim of a cup, the hand of another person, the bark of a tree, the cool tile of a kitchen floor at an hour when no one should really be in the kitchen, but somehow there we are. Touch seems immediate. It seems like the most direct relation we have with the physical world. Sight can be deceived, sound can echo, memory can drift, but touch feels definite. Either your hand is on the table or it is not. Either your foot has reached the floor or it has not. If there is any part of life that ought to feel perfectly grounded in simple reality, it is probably this. And yet, once again, the ordinary fact turns out to be hiding a very odd mechanism. The sensation of touch is not the simple meeting of two solid surfaces in the old everyday sense. It is not little hard atoms from your skin pressing directly against little hard atoms in the table until they make tiny contact in the way pebbles touch in a jar. What you experience as touch is a large-scale summary of something more subtle. Your skin approaches another material. The atoms in your skin and the atoms in that material begin to interact strongly through their electrons and their electric charges. Further overlap becomes energetically unfavourable. Your tissues deform a little. Specialised receptors in the skin respond to pressure, stretch, vibration and texture. Signals travel through nerves to the brain. The brain assembles all of that into the rich and confident experience we call touching something. So the first surprise is that touch is not just out there in the world. It is partly inside you. It is a constructed sensation, though constructed does not mean fake, it means translated. There is an event at the boundary between your body and the object, and your nervous system interprets that event into an experience with qualities like hardness, smoothness, softness, warmth, sharpness, and weight. That translation is so quick and so reliable that it feels invisible. You do not notice your brain building the sensation any more than you notice your eyes, quietly stitching together a stable visual world from shifting streams of light. You just feel the table. You just feel the wall. You just feel the pressure of the pillow under your head. That word pressure is worth lingering over, because pressure is one of the most ordinary forms of the world speaking back to you. When you sit in a chair, you feel pressure where the chair supports you. When you lie down, you feel pressure distributed through the mattress. When you hold a pen, your fingers feel the pressure of its surface against the skin. When your shoes meet the ground, there is pressure between foot and floor at every step. Pressure is the bodily language of support and resistance. It is how the world tells your body that it is there and not willing to be occupied in the same way at the same time. At the human scale, pressure seems easy to understand. One thing pushes on another. But at the atomic scale, what does that pushing consist of? It is not the old story of tiny hard particles knocking like miniature billiard balls. It is the story of charged quantum systems approaching and resisting further overlap. As the outer electrons of the atoms in your skin come near the outer electrons of the atoms in the object, electromagnetic forces become very important. The exclusion principle becomes important too, because the electrons cannot all be arranged arbitrarily. The system resists being compressed into forbidden or strongly unfavourable states. That resistance shows up at your scale as a force distributed over an area. Your body reads that distribution as pressure. This is where contact begins to look almost like an illusion, though illusion needs to be handled carefully here. It does not mean nothing is happening. Quite the opposite. A great deal is happening. What it means is that the simple picture we carry in our heads is wrong. We imagine surfaces meeting directly, as though one solid thing comes right up against another solid thing, and there the matter rests. In reality, what we call contact is the point at which further easy approach is prevented by the interactions of the atoms involved. Your hand does not need to sink into the table until some ultimate point of literal touching has been reached. The mutual resistance of their electron structures is enough. What you feel is not a naive physical kiss between tiny hard edges. It is a boundary of prohibition translated into sensation. That is such a strange sentence that it deserves a little patience. A boundary of prohibition translated into sensation. It sounds more dramatic than a coffee mug deserves, and yet it is what is happening. The mug says no to the hand in the language of electromagnetic interaction and quantum exclusion. The hand says no to the mug in exactly the same language. The result is a stable boundary between them. And because your skin and nervous system are exquisitely sensitive to deformation and force, the boundary becomes a feeling. The world does not simply stop you. It lets you know that it has stopped you. There is something almost intimate about that. Touch feels like closeness, and in one sense it is. When you touch something, your body and the object are interacting strongly enough for the boundary between them to matter in immediate sensory detail. But it is also a kind of well-organised refusal. You do not merge with the table. You do not drift into the wall. You're brought up against a limit, and the limit is what you feel. Touch is closeness without overlap. It is relation without interpenetration. It is the experience of getting near enough for the hidden rules of matter to become personal. This also explains why different materials feel so different even though, at bottom, all of them are made of atoms. Silk feels different from stone. A metal railing feels different from a wool sleeve. Glass feels different from bark. Bark from skin. Skin from paper. Paper from ceramic. Ceramic from bread crust. Some of these differences come from texture on relatively large scales. Some come from thermal properties, because materials conduct heat away from your skin at different rates, and your brain interprets that as warm or cool. Some come from how the material deforms under pressure. Some come from microscopic structure. But in every case, the feeling is a report about how your body and that material interact at the boundary. The smoothness of glass is not a mystical property. It is the result of a surface with very little texture at the scale your skin can easily detect. The softness of a pillow is not a simple lack of solidity. It is a material structure that deforms readily under your weight while still providing support through countless microscopic interactions. The hardness of stone is not mere stubbornness. Stone is not. It is a strong resistance to deformation because of how the atoms are bound and arranged. The coolness of a metal spoon on the tongue is not because the spoon contains more coal than wood does. It is because metal conducts heat away from your body more efficiently, and your nervous system interprets that flow as cold. Touch, then, is not one sense, but a whole conversation composed of many kinds of information. Pressure sits at the centre of that conversation, because it is what happens whenever matter resists the occupancy of matter. You can feel it clearly by pressing a finger into your palm. At first there is a light sensation, then a stronger one as the tissues deform more. Press harder, and the sensation becomes sharp, then uncomfortable, then painful if you keep going. Which is your body making a very reasonable case for moderation. What is being detected here is not tiny contact points, in the simplistic sense, but the mechanical consequences of one structured body being forced against another. Cells compress, skin stretches, receptors fire. The experience of pressure is the mind reading the local geometry of resistance. That local geometry is also why pressure can be gentle or severe. Spread your body over a mattress and the force is distributed across a wide area, so the pressure at any one point may remain comfortable. Stand on a small stone hidden in the grass and the same body weight concentrated over a tiny area becomes a sharp and memorable objection. Pressure depends on area because what matters is how much force is concentrated where. But beneath that practical fact lies the same atomic story. The material does not yield indefinitely. The body does not pass through. Boundaries are enforced. Pressure is the felt expression of that enforcement. There is another layer of strangeness here. Even though we speak of surfaces touching, the relevant interactions are carried by fields and quantum behavior rather than by some final act of miniature physical bumping. In classical thinking, one might imagine that objects must literally come into contact at a precise point. Modern physics gives a more subtle account. The charged particles in matter influence one another through electromagnetic interaction. The electron structures of atoms overlap in ways that become strongly unfavourable. The exclusion principle constrains the available arrangements. It is from all of that that the apparent solidity of the surface emerges. So when you say your hand is on the table, you're saying something perfectly reasonable at the human level, but the deeper story is not one of tiny pebbles finally arriving at a last little line of direct contact. This does not make touch less real. If anything, it makes it more interesting. The reality of touch lies not in the simplicity of our picture, but in the reliability of the process. Every time you set down a book, close a door, stroke the sleeve of a coat, or lean your forehead against a cool window, your body is entering into the same kind of interaction with matter. The boundary forms, the resistance arises, the sensory system reports, the brain interprets, the world becomes tangible. This is not an illusion in the sense of deception. It is an illusion only in the sense that the surface story conceals the deeper mechanism. You can see this especially clearly in the case of pain. Pain is often the body informing you that pressure or deformation has reached a level likely to damage tissue. A sharp object concentrates force over a very small area and can break the usual integrity of the skin. A blunt object spreads force more widely, but can still cause injury if intense enough. Heat can alter molecular structures in tissue. Cold can do damage too. In every case, what matters is how physical interactions at the boundary affect the body. Pain is the urgent version of touch, the version that says this is no longer just information. This matters now. Even here, though, the deeper mechanism still depends on the same basic truth. Matter resists, boundaries hold, forces distribute, and the nervous system turns physical interactions into experience. There is also something deeply human in the way touch anchors us in reality. We trust what we can feel. A child reassures itself by holding a blanket. A tired person leans on a countertop. A grieving person reaches for another hand. Touch gives certainty because it feels immediate and mutual. Yet beneath that emotional and bodily certainty is a process built from invisible particles that never quite do what common sense imagined. You are not touching another hand because two continuous substances have merged at the boundary. You are feeling the resistance, warmth, texture, and slight movement of another structured body meeting yours. That sounds colder when described in physics language, but in practice it is not cold at all. It is the mechanism through which tenderness becomes physically possible. In fact, the illusion of direct contact may be part of what makes touch so psychologically powerful. The brain presents the event to you as immediate presence. Here is the cup. Here is the blanket. Here is the arm of the chair. Here is the hand you are holding. It does not present you with a technical summary of electromagnetic interaction, electron cloud overlap, receptor response, and cortical integration. That would be exhausting. Instead, it delivers the finished experience, smooth and convincing. The simplicity of touch is a user-friendly interface laid over some very complicated physics. This is true of much of perception, of course. but touch feels especially honest, which is why its hidden complexity is so delightful. Sight can misjudge distance. Hearing can be fooled by echoes and expectation, but touch seems plain. It seems to say, here, undeniably, is a thing. Yet even here the thing arrives as interpretation. You do not detect matter directly in all its microscopic detail. You detect what your body can register about the interaction. Pressure, texture, temperature, vibration, movement. The rest is assembled into a world that feels continuous and solid. Nature gives you the result, not the raw accounting, and because the result is so stable, it becomes easy to forget how much of life depends on it. Every practical skill you possess depends on controlled touch and pressure. Walking depends on feeling the ground and adjusting force. Writing depends on fine pressure between fingers and pen. Eating depends on lips, tongue, hands, teeth, utensils, all engaged in exquisitely coordinated contact. Sleep depends on the way blankets settle, mattresses support, pillows yield, and the body gradually trusts the surfaces around it enough to rest. Even something as simple as turning a page requires a choreography of friction, pressure, and tactile feedback so ordinary that it disappears into habit. But habit should not make us dismissive. The world of touch is a triumph of organized matter. It is what the exclusion principle and electromagnetic interaction feel like when translated into the language of living tissue. That is why you can trust a chair to hold you, a floor to stop you, a handrail to push back, a doorknob to meet your grip. These are not separate miracles. They are many versions of the same underlying order. Matter resists overlap. Bodies detect the resistance. Minds call it contact. It is also why the phrase illusion of contact is both true and a little unfair. There is no literal deception in the everyday sense. You're not mistaken that the table is there. You're not hallucinating the wall. The illusion lies only in the simplicity of the mental picture. The world we feel is a simplified rendering of the world that physics describes. A useful rendering, a beautiful one, but not the final story. What looks like plain contact is actually an elegant negotiation at the boundary between organized systems of matter. Your fingertip and the table never become one thing. They arrive at the edge of what the laws of nature will allow, and once you start to see touch that way, something else becomes clear. The same hidden rule that explains why surfaces resist also explains why matter can build larger structures at all. If electrons did not obey exclusion, if atoms had no ordered extension, if material boundaries were not enforced in this deeply consistent way, then there would be no stable objects to touch in the first place. No tables, no teacups, no bones, no skin, no furniture with strong opinions about where your knee should not go. The world of touch exists because the world of matter has structure. And the world of matter has structure because certain particles are not allowed to occupy the same states. So the next thing to notice is not just that contact is an organized refusal, but that this refusal is exactly what builds the ordinary objects around you, and even the shape of the body doing the touching. Once you see touch as the felt edge of matter resisting overlap, the next step is almost unavoidable. If that resistance is happening everywhere, all the time, then it is doing more than stopping your hand at the wall. It is participating in the construction of the entire ordinary world, not by itself, and not in some magical one word explains everything sense, but as one of the central rules that allows matter to become stable, differentiated, and useful. This is where the Pauli Exclusion principle stops looking like a specialist detail about electrons and starts looking like part of the hidden carpentry of reality. It helps build tables, it helps build teacups, it helps build trees, books, spoons, lungs, fingernails, pillows, floorboards, and the body you happen to be occupying while listening to all this. That may sound like a lot of responsibility for one principle, but the chain of consequences is actually very direct once you follow it slowly. Electrons in atoms are not free to all pile into the same state. Because of that, atoms acquire structure. Because atoms acquire structure, they have characteristic outer electron arrangements. Because those outer arrangements differ from element to element, chemistry becomes varied. Because chemistry becomes varied, atoms can join into molecules and materials with very different properties. Because materials can differ, the world can contain wood and steel and wool and water and bone instead of one monotonous universal substance. Exclusion is not the whole story, but it is one of the reasons there is a story at all. Take something simple, like a wooden table. It looks solid and familiar enough that it's easy to forget how much has to go right for such a thing to exist. The wood is made of molecules built mostly from carbon, hydrogen, and oxygen. Those atoms bond in highly specific ways. The molecules arrange into long structural systems that give the wood strength, grain, flexibility, and weakness in different directions. The table can bear weight because those structures resist deformation. The atoms within them maintain stable relations because of the behavior of electrons. The electrons behave as they do because quantum rules determine what states they may occupy. The exclusion principle is there near the beginning, forcing structure into atomic life, which then expands outward into chemistry, and finally into the quiet confidence of a table holding a lamp. The same is true of a teacup, though the material story differs. A ceramic cup is not wood. It has a different internal arrangement, different bonds, different mechanical character. It is hard, somewhat brittle, good at containing liquid, bad at surviving sudden meetings with tiled floors. Those properties come from the way its atoms are organized after shaping and firing. The material can keep its form because the electrons in the atoms do not permit arbitrary collapse into sameness. The atoms can bind in a network because their outer electron arrangements make that possible. The whole object stands on a foundation of quantum order. So when you lift a teacup and trust it not to pass through your hand, you're relying on a principle first noticed in atomic physics to keep breakfast from becoming a much more liquid event. What is especially satisfying is that exclusion does not merely build objects in the sense of giving them shape. It also helps make them distinct. A table is not just a lump. A teacup is not just a hardened puddle. Objects keep boundaries because matter maintains arrangements. The atoms in the table do not suddenly decide to become part of the air. The cup does not quietly dissolve into a featureless blur while you're not looking. Stable objects exist because their constituent matter is constrained into certain organizations and not others. At every level, from the atom upward, the world is full of rules about what may combine, what may repeat, and what may not. This becomes even more striking when you turn from furniture to life. It is one thing to say the exclusion principle helps give form to a chair. It is another to realize that the same hidden rule contributes to the existence of skin, muscle, blood, and bone. Your body is not a vague bag of warm chemistry held together by optimism. It is a highly structured material system. Proteins fold into very particular shapes. Cell membranes form boundaries. Collagen gives tensile strength. Bone combines mineral hardness with a living framework. DNA stores information in molecular form. Every one of these achievements depends on chemistry, and chemistry depends on electron structure, and electron structure depends in part on exclusion. Consider bone for a moment. It feels so ordinary when it is doing its job properly that we mostly notice it only when it fails, usually in dramatic and expensive ways. But bone is a remarkable material. It is strong enough to support the body, light enough to allow movement, dynamic enough to be constantly remodeled by living cells, and structured enough to resist stresses in daily life. None of that happens by accident. The mineral and organic components of bone are built from atoms arranged through chemical bonds. Those bonds arise from electron behavior. Electron behavior arises within a world constrained by quantum rules. The skeleton is not a primitive support beam dropped into biology from nowhere. It is a biological expression of atomic order. Skin offers another example, almost the opposite in feel but no less rich. Skin is soft compared with bone, flexible compared with ceramic, warm and living compared with furniture, but it is still matter with boundaries. It stretches, heals, senses, protects, and negotiates constantly with the outside world. The molecules in skin, the fats and proteins and water and salts that give it its character, all depend on chemical structures whose possibility begins in atomic arrangement. The fact that your skin can press against a blanket and feel comfort, rather than simply dispersing into the fabric, is a consequence of matter having organized form. Exclusion is buried deep beneath that comfort, but it is there, and perhaps that is the main theme here. The Pauli exclusion principle does not show itself directly in daily life. It hides behind layers of consequence. It does not announce itself when you pick up a spoon. It does not whisper from the staircase. It does not glow faintly in the cupboard beside the plates. Instead, it does something more impressive. It disappears into the normal functioning of reality. It becomes part of the reason things exist as things. The better it does its job, the less anyone notices it, which is often how the most important physical rules behave. There is also a useful correction to make here. It would be too simple to say exclusion builds matter all by itself. Matter is built through electromagnetic interaction as well. Atoms bond because of the attraction and arrangement of charged particles. Molecules take shape because of the energy balance of electron configurations. Materials acquire strength because of the collective behavior of countless atoms and molecules. Exclusion is not the only actor on the stage, but it is one of the rules that determines what kinds of atomic arrangements are possible in the first place. It gives matter room to be structured. It prevents electrons from collapsing into sameness. Without it, chemistry would not have the same richness, and the material world would lose the complexity that makes objects and bodies possible. This is easiest to appreciate when you think about carbon again, because carbon is one of the great workhorses of visible complexity. Carbon can form stable bonds in many directions and patterns. That versatility makes long chains, rings, frameworks, and the enormous molecular diversity of life possible. Proteins, fats, sugars, nucleic acids, all of them depend heavily on carbon chemistry, but carbon behaves that way because of the arrangement of its electrons, and those electrons occupy their states according to quantum rules that include exclusion. So the principle does not merely help build inanimate objects, it also helps make biochemistry possible. The line from quantum restriction to consciousness is long, but it is real. Somewhere near the beginning of the story, electrons refuse to share identical states, and much later a person lay in bed wondering why walls are so unsympathetic. There is something almost comic in that scale difference. The same rule that shapes electron structure in atoms is involved in the existence of the neurons doing the wondering. Physics often works like that. It gives you a tiny principle, and then lets you discover that it echoes upward through layers of organization until it reaches the scale of rooms, forests, bodies, and weather. Nothing in the ordinary appearance of a teacup suggests that its reliability depends on quantum mechanics. Nothing about a wooden chair says, at first glance, I am made possible by fermions obeying a restriction on state occupancy. And yet here we are. One of the clearest ways exclusion helps build the everyday world is by making matter occupy space in a structured way. Atoms have extent because their electrons fill allowed states rather than collapsing into one. Those atoms then approach other atoms with their own electron structures already in place. The result is not random mixing. It is patterned bonding where permitted, resistance where not, and material forms emerging from both. This is why a crystal can grow with orderly geometry, why a metal can conduct, why rubber can stretch, why a brick can support weight, and why your hand and the brick do not simply decide to combine into an awkward compromise. Even softness depends on exclusion. It is tempting to think only hard things reveal the principle, because walls and tables are the dramatic examples, but a blanket also occupies space. A loaf of bread also has form. A body lying on a mattress is supported not by hardness alone, but by organized matter, yielding and resisting in controlled ways. A pillow can compress because its structure allows rearrangement under load, but not total disappearance. The fibres, foams, or feathers still take up space. Their atoms still obey the same underlying rules. So exclusion does not just build the hard edges of the world, it helps build the whole range of material behaviour from stiff to springy to soft. That range matters a great deal for life. A world made only of rigid solids would be unlivable in one direction. A world made only of shapeless fluids would be unlivable in another. What makes ordinary life possible is the enormous variety of materials produced by atomic and molecular structure. Bone is hard. Tendon is strong and flexible. Muscle is contractile. Blood flows. Skin bends. Hair stretches a little and breaks only after protest. Wood can be carved. Clay can be shaped and then hardened. Wool insulates. Cotton breathes. Glass transmits light while remaining mostly firm and unforgiving. These are not random perks. They are the visible consequences of chemistry, and chemistry depends on the architecture created by quantum rules. Your body is especially interesting because it is not just one material, but a community of materials, all coordinated. The enamel on your teeth is not like the tissue of your liver. The membranes of your cells are not like the collagen in your tendons. The hemoglobin in your blood behaves differently from the lipids in your skin, yet all of them depend on the same underlying physical grammar. Atoms with structured electron arrangements form molecules. Molecules form larger organized systems. Those systems become tissues. Tissues become organs. Organs become a body able to move through the world, touch it, be stopped by it, and think about why. That last part is still one of the strangest. A principle that helps determine atomic structure also helps make the very organism capable of asking what atomic structure is. It is difficult not to enjoy that. The universe arranges matter according to deep rules, and eventually some of that matter becomes curious enough to investigate the arrangement. Exclusion is therefore not just part of the story of objects around you. It is part of the story of the thinker asking the question. It helped build the body, it helped build the brain, it helped build the molecules that let brain cells signal one another. It helped build the surfaces of the eyes reading or the ears listening. Quantum discipline grows into self-awareness by way of chemistry and biology. Of course, none of this means the exclusion principle is the secret essence of personhood. Physics is not in the business of turning people into slogans. A human being is not just a pile of quantum states with opinions. There are many levels of explanation between electrons and a personality, between atomic structure and a life. But it's still true that without exclusion there would be no stable atoms of the right sort, no rich chemistry, no tissues, no organs, no nervous system, and no person. The ordinary human shape is one of the large-scale achievements of small-scale rules. This is why the phrase builds tables, teacups, and you is not just a cheerful exaggeration. It is a compact summary of the enormous reach of a single physical principle. The table exists because matter can become a stable solid with structure. The teacup exists because atoms can bond into a ceramic network with hardness and shape. You exist because chemistry can become complicated enough to support life, and life can become organized enough to support a conscious body. In every case, exclusion is part of the reason the required atomic structure is possible. There is another practical consequence of this worth noticing. Because matter is built in this structured way, the world is not only made of objects but also made of separations. The table is not the cup. The cup is not your hand. Your hand is not the air. The air is not the wall. Boundaries are everywhere. Some are sharp, some are soft, some are porous, some are dynamic, but none of them are arbitrary. They emerge from material organization. This is why the world feels divided into usable things rather than existing as one continuous undifferentiated mass. Exclusion, working together with other physical laws, helps give reality joints, and once reality has joints, it can support all the ordinary acts of living. You can sit because chair and body remain distinct yet interacting. You can drink because cup and liquid and hand keep their identities while meeting in controlled ways. You can walk because floor and foot exchange force without merging. You can breathe because the molecules involved in respiration have exactly the chemical behavior they do. You can think because nerve cells maintain electrical and chemical organization over time. The deep order of matter is not an abstract luxury. It is the basis of ordinary function. Perhaps the most impressive part of all this is how quiet it is. The world does not feel like a triumph of quantum rules. It feels normal. The spoon is where you left it. The blanket still works. The bones in your feet continue the thankless task of supporting your late evening decisions. The table holds the lamp. The cup contains the tea. Reality behaves with enough consistency that you're free to forget what produces that consistency. That forgetfulness is understandable, but it's also why subjects like this are so satisfying. They return strangeness to the familiar without making it unusable. So when we say exclusion builds tables, teacups, and you, what we really mean is that the visible world is the result of hidden restrictions made fruitful. Electrons cannot all be the same in the same state. Because they cannot, atoms become structured. Because atoms become structured, chemistry becomes rich. Because chemistry becomes rich, materials and life become possible. The rule is negative in form but positive in consequence. It says no at one level and creates abundance at another. And if that already sounds impressive at the scale of household objects and living bodies, it becomes even more striking when you follow the same principle into places where matter is pushed far beyond everyday conditions, because the same exclusion that helps keep a teacup in shape also helps certain stars resist collapse under their own enormous weight. The scale changes now, but the rule does not. That is one of the most satisfying things about physics. A principle first noticed while trying to understand electrons in atoms does not stay politely confined to the atom. It follows matter wherever matter goes. It shapes chemistry in the kitchen and structure in the body, and then, with the same steady indifference to our sense of proportion, it turns up inside stars. The same kind of quantum refusal that helps keep your hand from passing through a wall also becomes part of the reason certain stars do not collapse completely under their own gravity. The universe has a way of taking what seems like a local rule and revealing that it was never local at all. Gravity, of course, is the great collector. Left to itself, it gathers matter inward. It pulls gas into clouds, clouds into denser clouds, dense clouds into stars. It keeps planets together. It draws rain downward, bodies to the ground, oceans into curves around the world. It is patient and relentless, and not especially interested in whether the material it is compressing would prefer a little more room. If all you knew about a star was that it contained an enormous amount of matter and that gravity pulls matter inward, you might assume the story ends with endless collapse. Why should it not? Why should a star not simply keep squeezing itself smaller and smaller forever? But stars are not sacks of passively obedient substance. They are matter, and matter has rules. During most of a star's life, one of the main things pushing back against gravity is the energy released by nuclear fusion in the core. The star shines because fusion is happening, and that same process helps hold the star up. Gravity pulls inward. Pressure from the hot interior pushes outward. For long stretches of cosmic time, there is a balance. The star lives in that balance. It glows. It radiates. It spends its fuel with the magnificent calm of something that does not need to hurry because it has already committed itself to millions or billions of years. Eventually, though, the easy fuel runs low. The details depend on the mass of the star, because stars are not all destined for the same old age. Some live gently and die gently. Some live fast and end with theatrical violence. But for many stars, the crucial point arrives when the thermal pressure from fusion is no longer enough to keep gravity fully at bay. Gravity then begins to win more of the argument. The core contracts. Conditions change. In some cases, new fusion stages occur. In others, the star sheds outer layers and leaves behind a dense remnant. And it is in those remnants that the exclusion principle steps onto the stage with almost startling importance. Take a white dwarf. A white dwarf is what remains after a star like the Sun has finished the main part of its life and cast off its outer layers. What is left is extraordinarily dense. Not dense in the casual sense of a book being denser than a pillow, but dense in the sense that a great deal of mass is packed into a volume not much larger than a planet. A white dwarf no longer supports itself by ongoing fusion in the ordinary way. It does not need that old engine anymore. Instead, what resists further collapse is largely a quantum effect connected to the electrons. This is where the exclusion principle becomes more than part of the background story. It becomes the central support. As gravity squeezes matter inward, electrons are forced into closer quarters. But electrons are fermions. They cannot all occupy the same quantum states. That simple fact has a dramatic consequence under extreme compression. The more tightly you try to squeeze the matter, the more the electrons are forced into different and increasingly energetic allowed states. This creates a pressure that does not depend in the same way on ordinary heat. It is often called electron degeneracy pressure, though the name sounds a bit unfortunate if you're not already in the habit of forgiving physics its terminology. Nothing morally degenerate is happening. It simply means the pressure arises from the way many electrons fill available states under quantum rules. What matters is that gravity cannot just push the electrons into one shared arrangement and be done with it. The states are already filled in accordance with exclusion. To compress the star further is to demand ever more extreme rearrangement into higher allowed states. The matter resists. The star pushes back. And so a white dwarf can exist as a stable object, not because it is still merrily burning fuel in the old stellar way, but because quantum mechanics has supplied a new kind of support. In a sense, the star is being held up by the refusal of electrons to become too similar in the same state. There is something wonderful about that. A white dwarf is not upheld by heat alone, nor by some hidden cosmic column, nor by a renewed burst of nuclear enthusiasm. It is upheld by a rule you have already met in atoms and solids. The scale has changed almost absurdly, but the logic is familiar. Matter resists being compressed into forbidden sameness. At the scale of a tabletop that helps explain solidity. At the scale of a dead star, it helps explain survival against collapse. The same refusal that makes objects occupy space in your room becomes, under gravity's more severe persuasion, a star's last line of defense. This was one of the great realizations of modern astrophysics. It told us that quantum mechanics was not only the language of atoms and spectra and tiny particles in laboratory thought experiments. It was also the language of stellar corpses. The universe was not divided into small-scale quantum weirdness and large-scale, respectable astronomy. The two belong to one another. A star dying in deep space and an electron refusing a duplicate state in an atom are not separate kinds of truth. They are different scales of the same truth. White dwarfs, then, are one of the most elegant examples of quantum rules becoming astrophysical architecture. But elegance rarely means infinite freedom. Electron degeneracy pressure can support a star only up to a point. If the remnant is too massive, gravity becomes too strong for that electron-based support to hold indefinitely. There is a limit. This too is part of the beauty of physics. Nature often allows stability, but only within conditions. Beyond those conditions, new things happen. That limit became famous through the work of Subrahmanyan Chandrasekhar, who showed that above a certain mass, a white dwarf can no longer be supported by electron degeneracy pressure alone. The details are subtle and involve relativity as well as quantum mechanics, but the broad story is clear enough without turning the night into a mathematical exam. If the remnant is light enough, electron degeneracy pressure wins and the white dwarf endures. If it is too massive, gravity pushes past what that pressure can sustain. The star must continue its collapse into something even more extreme. And here the story becomes more dramatic without becoming less calm. Matter under such pressure is no longer content to remain in its familiar atomic form. The compression becomes so intense that electrons and protons can combine in ways that transform the character of the matter itself. The result, in the right circumstances, is a neutron star. If a white dwarf is an astonishing density made possible by the resistance of electrons, a neutron star is what happens when gravity drives the matter into an even more severe regime, where another quantum rule-based support takes over. Neutrons, like electrons, are fermions. They too obey exclusion. So in a neutron star, a related but even more extreme form of degeneracy pressure helps resist gravity. The star becomes smaller, denser, more intense in almost every way. A neutron star can pack more mass than the Sun into a sphere perhaps only the size of a city. That sentence still sounds like science fiction no matter how often one hears it. A city-sized star. Matter compressed so brutally that the familiar atomic structure has largely disappeared. And yet even there, the world is not free to collapse without resistance, because quantum rules continue to say no in the face of gravity's demand for less and less space. It is difficult not to admire the severity of the situation. Gravity keeps saying inward. Quantum mechanics keeps saying not without limit. The star is the place where those imperatives meet. In a normal solid object, the struggle is gentle by comparison. In a star, the same logic is turned up to cosmic intensity, and still the principle holds. Identical fermions cannot all occupy the same state. That rule remains calm and absolute whether it is contributing to the shape of an atom or helping support a stellar remnant against gravitational collapse. There is also something philosophically satisfying about the fact that stars, those ancient symbols of distance and grandeur, depend in part on the same microscopic order that shapes a teacup. Human beings have often imagined the heavens as governed by cleaner, nobler laws than the mundane world below. Modern physics has done something more interesting. It has unified them. The same universe that governs dust on a shelf governs the life cycle of stars. The same matter that makes up your bones and skin makes up stellar remnants. The same exclusion principle that helps define atomic structure is operating in objects so dense and strange that ordinary language begins to look unprepared. This unity also changes how we think about size. We're used to treating the tiny and the enormous as morally separate categories. Small things are one world, stars are another. But scale in physics is not a barrier to principle. A law can begin in the microscopic and become decisive in the macroscopic if enough matter is involved. In fact, the more matter you gather, the more crucial the underlying rules can become, because their consequences accumulate. A star is not exempt from quantum mechanics because it is big. If anything, under the right conditions, it becomes one of the most spectacular demonstrations of quantum mechanics in the entire universe. There is a further layer to the story that makes it even more impressive. Degeneracy pressure is not like ordinary pressure from heat in the everyday sense. A hot gas pushes outward because particles are moving energetically. Cool the gas, and that pressure drops. But degeneracy pressure comes from the occupancy of quantum states. It can remain important even when the object is not supported primarily by thermal agitation in the familiar way. This is why a white dwarf can gradually cool and still remain supported. Its structure is not waiting anxiously for warmth to save it. The support is written more deeply into the quantum organization of the matter. That is almost a hauntingly beautiful idea. A star that has exhausted the old fire, yet is still held up by the silent insistence of fermions on distinct states. The drama of blazing fusion gives way to the restraint of exclusion. It is as though the universe changes tactics but not commitment. The star no longer lives in the same way, but it does not simply fall apart. It becomes a relic sustained by principle. Neutron stars take this severity even further. Their gravity is immense. Their matter is so compressed that our ordinary intuitions about solids, fluids, and atomic structure become poor guides. And yet even there, order does not vanish, it changes form. Quantum statistics, nuclear forces, and extreme density create a new kind of matter with its own extraordinary properties. The star spins, radiates, sometimes beams, pulses through space, and endures because total collapse is still being resisted. Not forever in every possible case, of course. If enough mass is present, even neutron degeneracy and related effects will not be enough. Then gravity may continue toward the formation of a black hole. Physics does not promise rescue under all conditions, but it does provide stages of resistance, and those stages are built from deep rules. That escalation from white dwarf to neutron star to black hole is one of the clearest examples of how the universe tests the limits of its own organizing principles. First electron degeneracy holds, then beyond that, it fails. Then neutron-based support may hold. Beyond that, perhaps not. It is almost architectural in its sequence, as though matter carries different hidden braces for different levels of stress, and each brace is rooted in what particles are allowed to do. What I like most in this whole part of the story is that it rescues quantum mechanics from the common complaint that it only matters in weird, tiny situations far removed from life. Here, quantum mechanics is holding up stars, not in a decorative or metaphorical sense, literally helping determine whether a stellar remnant stands against gravity or collapses further.
One could hardly ask for a better reply to the suggestion that the quantum world is somehow too small to matter. The quantum world is why some stars remain stars of a particular kind at all. It also tells us something reassuringly general about matter. Matter has structure not only at comfortable densities, but under astonishing stress. The same rules that create order in atoms become bulwarks under pressure. The universe is not improvising support from nowhere. It is drawing on the same hidden grammar again and again. A star is not a special exception to the rules that shape ordinary matter. It is one of their grandest expressions. And because this is still the same story, we began within the room around you. The connection is worth stating plainly. Why can you not walk through walls? Because matter occupies space through atomic structure and resists overlap through electromagnetic interaction and exclusion. Why does a white dwarf not collapse further? Because under immense gravity, electrons still obey exclusion and produce degeneracy pressure. Why can a neutron star exist at all? Because even after matter is driven into a far more extreme state, fermions still refuse unrestricted sameness. The logic is continuous. The setting changes. The stakes change. The principle stays itself. That continuity is one of the deepest pleasures in physics. A law does not become less true when the scene grows larger. It becomes more astonishing.
The atoms in your hand, the ceramic of a teacup, the carbon chemistry of your body, the dense remnant of a dead star, all belong to one order. Once you understand that, the ordinary and the cosmic stop feeling like separate subjects. They become neighbours. Still, stars are not only places where laws hold. They are also places where nature reveals its edge cases, its strained limits, its stranger allowances. Extreme environments have a way of showing that rules can produce outcomes we would never guess from daily life. A particle may sometimes do what a large object practically never does. A barrier that seems absolute at one scale can become permeable in another context. So after seeing quantum rules hold up the stars with such stern consistency, it becomes natural to ask whether the quantum world ever permits smaller, stranger departures from ordinary common sense, because that is where the story bends toward tunneling, rare escapes, and the peculiar exceptions that never quite amount to walking through the living room wall, but are no less real for that. That is where the story relaxes its grip a little, not because the wall is about to become cooperative, but because quantum mechanics has a habit of saying something impossible in ordinary life, and then quietly adding, except in these rather specific circumstances. We have spent a long time building the case for why matter resists overlap, why atoms take up space, why electrons obey exclusion, why touch is really the sensation of organized refusal, and why even stars can be supported by the same underlying logic. All of that is true. It remains true. And yet there is another side to the quantum world, a side that seems to enjoy unsettling any picture that becomes too tidy. if exclusion tells you that particles cannot simply all share the same state, tunneling tells you that a particle confronted with a barrier does not always behave like a tiny classical object bouncing back in defeat. Sometimes it appears on the other side. This is one of those facts that sounds at first like either a misunderstanding or a prank played by the universe on common sense. In ordinary life, barriers are barriers. A ball thrown at a wall rebounds or stops. A person walking into a door has a chance to learn a lesson. Water in a sealed glass remains in the glass unless the glass itself fails or is turned upside down by someone who is overconfident about the table edge. Classical thinking trains us to expect that if an object does not have enough energy to cross a barrier, it simply does not cross. It is a clean rule and a practical one. Most of the visible world behaves that way at our scale, but quantum mechanics is not classical thinking with more difficult homework. It is a different description of reality at small scales. In that description, particles are not little pellets with sharply defined paths in the old sense. They are described by quantum states that can spread, interfere, and behave in ways that do not map neatly onto the language of miniature billiard balls. A barrier in quantum mechanics is still a barrier. It still matters. It still changes what is likely and what is allowed. But it does not always impose an absolute no in the same way a wall does for a moving football or a distracted human forehead. There can be a non-zero chance that a particle will be found on the far side of a barrier even when the simple classical picture says it should not get through. That phenomenon is quantum tunneling. The name is helpful and misleading at the same time. It is helpful because it evokes the idea of passing through something that would otherwise block you. It is misleading because it encourages a very ordinary picture. One imagines a particle taking out a tiny shovel, putting on a hard hat, and burrowing neatly through the obstacle. That is not what happens. There is no miniature drilling operation. The barrier is not being physically excavated from the inside. Tunneling is a feature of the quantum description itself. The state of the particle does not simply stop dead at the barrier. Under the right conditions, there is still some amplitude associated with the far side, and therefore some probability of detection there. Even saying it that way risks sounding more mysterious than it needs to. The practical point is simpler. The barrier does not always make the probability of passage exactly zero. It can make the passage very unlikely, sometimes absurdly unlikely, but not always impossible. And that distinction between very unlikely and impossible is one of the deepest habits of the quantum world. It is forever taking human categories that seemed absolute and sanding down the edges until a subtle opening appears. Now, as soon as people hear this, one question tends to leap forward wearing a very hopeful expression. If particles can tunnel through barriers, then why can I not tunnel through a wall? Why does my body not occasionally find itself in the next room to the surprise of everyone involved? Why am I still required to use doors like a person trapped in ordinary reality? The answer is that while tunneling is real, the probability for a large macroscopic object made of an immense number of particles to tunnel through a wall as a whole is so unimaginably tiny that you should not rearrange your home around the possibility. It is not just unlikely in the way rain might interrupt a picnic.
It is unlikely in a way that makes waiting for it less practical than waiting for a mountain to get bored and migrate. The reason is not difficult to grasp in spirit, even if the precise mathematics can become severe. For a single small particle, tunneling through a barrier can have a measurable probability under the right conditions. For an object as large and complicated as a human body, the event would require an extraordinary coordination of vast numbers of particles behaving in exactly the right way relative to the barrier. The probabilities multiply into absurdity. Every atom in your body is part of a larger organized system. That system is warm, messy, interacting internally and externally, and not at all like a lone electron facing a thin barrier in a controlled experiment. So while tunneling is a genuine exception to naive classical impenetrability, it is not the loophole through walls that bedtime fantasy might have hoped for. Still, it is real enough to matter enormously in physics. In fact, some of the world would look very different without it. One of the earliest and most striking examples comes from nuclear physics. Certain atomic nuclei undergo radioactive decay by emitting particles, and one way to understand some of these decays is through tunneling. A particle inside the nucleus is not supposed, in the classical picture, to have enough energy to escape the barrier that confines it. Yet after some unpredictable waiting time, it appears outside.
The nucleus changes. Radiation is emitted. This is not because the particle somehow gathered a secret reserve of classical energy and sprinted out when no one was looking. It is because the quantum state allowed a small but genuine probability of escape through tunneling. That alone is a wonderful little rebellion against common sense. Something confined is not always absolutely confined. A barrier is not always perfect. The universe leaves itself narrow side doors, and these side doors are not decorative. They help explain observed phenomena. They are built into nature, not added later as a flourish for advanced students. There are atoms in the world whose behaviour depends on this strange permission. There are clocks based on radioactive processes. There are measurements, technologies, and histories of matter that quietly rely on a particle occasionally making a transition that classical life would have ruled out. Tunneling also appears in the heart of stars, which is especially pleasing after the previous part of our story. Stars are powered by nuclear fusion, and fusion itself would be far more difficult if particles had to rely only on classical expectations. Positively charged nuclei repel one another. That repulsion is a barrier. At the temperatures in stellar cores, particles move very fast, but not always in the way a simple classical account might demand for fusion to occur as often as it does. Quantum tunneling helps here too. It allows nuclei sometimes to get close enough to fuse, even when the classical story would be more discouraging. In other words, part of what makes stars shine is that the quantum world occasionally permits strange escapes and improbable arrivals. A star glows because particles do not behave like tiny respectable citizens, obeying only the rules of macroscopic intuition. That is one of my favourite features of tunneling. It sounds like a bizarre edge case, something that ought to matter only in the footnotes of obscure experiments. Yet it contributes to the operation of the stars. It helps power the sunlight that warms the planet, feeds plants, drives weather, and eventually becomes the energy in wood, bread, and human thought. The path from tunneling to morning light is long, but it exists. So even the exceptions are not marginal. They are woven into the functioning of the universe. The world of technology has also found ways to make use of tunneling. Certain electronic devices rely on it. There are components in modern circuits whose operation cannot be fully understood without quantum mechanical passage through barriers. And perhaps one of the most elegant examples is the scanning tunneling microscope. This instrument does something that would once have sounded like a feverish boast. It uses tunneling to probe surfaces at the level of individual atoms.
Bring a very fine tip extremely close to a conducting surface, close enough that the quantum conditions are right, and electrons can tunnel between tip and surface. The resulting current depends very sensitively on distance. Measure that current carefully while scanning, and one can reconstruct the topography of the surface with astonishing precision. There is something almost poetic in that, though I will resist becoming too poetic because you asked me not to drift into abstraction. A strange quantum exception becomes a practical measuring tool. We do not merely tolerate tunneling as a weird fact. We recruit it. We make it work for us. We turn a loophole in classical intuition into an instrument that reveals the atomic landscape of matter. That is science at its most satisfying. Nature presents a strange behavior, and instead of complaining that it is inconveniently strange, human beings eventually build a machine out of it. This does not mean tunneling is common in the everyday world in the way pressure, weight, and friction are common. It remains most obvious where scales are tiny, barriers are narrow, and quantum behavior has not been washed out by the complexity of large warm systems. That last point matters. The everyday world is crowded, noisy, thermally active, and composed of countless interacting particles.
Quantum effects do not disappear there, because without them matter would not exist in its familiar form at all. But many of the more dramatic quantum behaviors become hidden under the averaging and stability of macroscopic life. You are made of quantum matter, but you do not usually behave like an electron in a neat laboratory setup, and everyone around you is quietly grateful for that. Still, the existence of tunneling tells us something important about how to think about the principle we began with. When we say you cannot walk through walls, we are speaking at the human scale, where that statement is true in every practical sense that matters. But underneath it lies a subtler world in which barriers are not always absolute for individual particles. The wall is not metaphysically impenetrable in some perfect and final way. Rather, the organised matter of the wall and the organised matter of your body interact so overwhelmingly strongly, and the macroscopic tunnelling probability is so fantastically small that the wall functions as an absolute barrier for all practical life. That is a slightly less dramatic sentence than the old cartoon version, but it is more faithful to physics, and physics often prefers this sort of answer. Not impossible in the deepest mathematical sense, impossible for anything you will ever need to plan around. The universe is full of events that have non-zero probability and zero practical significance.
That may sound cynical, but it is actually one of the reasons ordinary life is stable. Doors remain useful. Houses keep their layout. You can place a mug on a shelf without worrying that it will quantum mechanically relocate to the sink in an act of microscopic rebellion. Reality allows oddities, but it does not do so recklessly. There are other strange escapes besides tunneling in the strict sense. Quantum mechanics is full of transitions that feel odd from a classical viewpoint. Particles can move between allowed states in atoms. Electrons can leave a material under the right conditions. Superconducting systems can display collective quantum behavior on scales larger than one might naively expect. Under carefully arranged conditions, matter can reveal a kind of coherence that ordinary experience does not prepare you for. But all of these cases come with conditions. They are not invitations to abandon the solidity of the everyday world. They are reminders that the everyday world is built on deeper rules that retain their own peculiar freedoms beneath the surface. One of the things I find most calming about this is that quantum mechanics is not inconsistent. It only feels that way when we try to force it into categories shaped by daily objects. At the human scale, the right statement is that walls are solid and you cannot walk through them.
At the microscopic scale, the more careful statement is that matter is made of particles and fields obeying quantum laws, some of which permit barrier penetration under certain conditions. These are not contradictory claims. They are different levels of description. The second explains why the first is so robust, and also why it is not philosophically absolute in the way common sense once assumed. And that distinction matters because it prevents us from sliding into two opposite mistakes. One mistake is to treat the ordinary world as if quantum mechanics never matters. That would be absurd because the structure of atoms, chemistry, materials, and solidity all depend on it. The other mistake is to hear about tunneling and imagine that ordinary objects are on the verge of dissolving into a carnival of improbable nonsense. That is equally wrong. Quantum mechanics does matter profoundly, but its strange permissions do not usually overthrow the organised stability of large-scale life. The world remains usable. Physics would be much less charming if every discovery ended with a recommendation to stop trusting chairs. There is also a deeper lesson here about barriers themselves. We like barriers to be absolute because that feels intellectually tidy. Either a thing can cross or it cannot. But nature is often more delicate than that. A barrier changes the landscape of possibility. It shapes probabilities. It may suppress passage so strongly that for all practical purposes passage never occurs, or it may leave a narrow channel through which some fraction of particles succeed. The barrier remains real, but reality is no longer a simple yes or no. It becomes a structured maybe, with numbers attached. That may be less emotionally satisfying than a crisp prohibition, but it is often how the world actually works. And because this whole story began with the impossibility of walking through walls, it is worth returning to that image with all the new complexity in place. Your body and the wall are both made of atoms. Those atoms have structured electron arrangements. The outer electrons of your body and of the wall interact strongly through electromagnetic forces. The exclusion principle prevents arbitrary overlap of identical fermions. At the scale of your hand, your arm, your torso, your entire body, the result is overwhelming resistance to passage. Quantum tunneling for the whole body exists only as an absurdly tiny formal possibility, not a practical mode of transportation, so the wall remains a wall. But now it remains a wall for more interesting reasons than you might have guessed when we began. There is a strange comfort in that. The universe is both stricter and more permissive than daily life suggests. Stricter, because the rules beneath matter are exacting and cannot be negotiated by wishful thinking.
More permissive, because beneath the strictness, there are subtle channels, rare processes, and quantum exceptions that make stars burn, nuclei decay, and advanced instruments possible. Reality says no with one hand and leaves itself delicate loopholes with the other. The balance is surprisingly elegant. If you sit with that balance for a while, the ordinary room around you starts to look richer again. The walls are not only barriers, they are achievements of organized matter. The air is not only emptiness, it is a sea of molecules obeying its own quiet rules. Your body is not just a passenger among objects. It is another structured system built from the same principles, sensitive to pressure, held together by chemistry, and alive enough to notice all this. The quantum world is not elsewhere. It is the hidden style in which the room is written. And that leaves us with a final turn that is less about exceptions and more about appreciation. Once you know that the world is held together by rules like exclusion, that solidity is the large-scale appearance of microscopic order, that even stars are supported by the refusal of fermions to pile into sameness, and that quantum loopholes exist without overthrowing daily life, the last thing to ask is what sort of principle this really is in the broader shape of reality. Because the Pauli Exclusion principle is not just a trick of atomic bookkeeping.
It is one of the quiet conditions that keeps the world from collapsing into monotony, and once you see that, it becomes possible to look at the ordinary existence of walls, tables, teacups, and your own body with a kind of calm gratitude for the hidden rule that keeps everything distinct. By now the rule has followed us a very long way. It began with a wall. It began with the ordinary fact that you cannot walk through one. Then it moved inward into atoms, outward into chemistry, upward into stars, and sideways into touch, pressure, and the stubborn reliability of furniture. Along the way, it kept doing something that the deepest ideas in physics often do. It kept turning out to matter more than it first seemed to. What looked like a narrow rule about electrons became part of the reason the visible world has shape, variety, support, and boundaries. And that is what makes it such a satisfying principle to sit with at the end. It is quiet. It does not announce itself in daily life, yet it helps keep the world intact. That phrase can sound larger than it needs to, so it is worth saying plainly what it means. The Pauli Exclusion principle helps prevent identical fermions, such as electrons, from occupying the same quantum state in the same system. Because of that, electrons in atoms fill different allowed states instead of collapsing into one. Because they fill different states, atoms acquire structure and size. Because atoms acquire structure and size, they interact in rich and specific ways. Because they interact in rich and specific ways, chemistry becomes possible in the form we know. Because chemistry becomes possible in that form, matter can become tables, cups, books, bones, skin, leaves, bricks, clouds of breath in cold air, and the body listening to this.
It is a long chain, but it is not a vague one. One quiet restriction becomes a very large amount of visible order. That is already impressive, but what makes the principle feel especially important is the kind of order it creates. It does not create a world of perfect sameness. Quite the opposite. It creates distinction, it creates layering, it creates the fact that one thing can be this and another thing can be that. Carbon can behave like carbon. Oxygen can behave like oxygen. Iron can act like iron. Wood can be wood and not glass. Skin can be skin and not stone. You can remain you and the chair can remain the chair without the two of you becoming a single confused event every time you sit down. The rule is negative in form, but its consequences are positive everywhere. It says that not everything may be arranged in the same way, and because of that, the world becomes varied instead of bland. There is something almost moral sounding about that, though physics is not making moral arguments. It is simply describing what kind of order matter obeys. Still, there is a pleasing human resonance to it. A world where every identical particle could collapse into the same lowest arrangement would be a world with far less character. The richness of matter depends on limits. The universe gets diversity by refusing total repetition. That is a good reminder that constraints are not always the enemies of complexity.
Very often, they are the reason complexity can exist in a stable form at all. When people first meet physics, there is a temptation to imagine that the deepest laws should be dramatic all the time. One expects black holes, explosions, strange paradoxes, and headlines with phrases like reality shattered. There is nothing wrong with those subjects. They are wonderful. But some of the most important laws are quieter than that. They do not break the world open. They hold it together. They do not astonish by spectacle alone. They astonish by reliability. The exclusion principle belongs to that family. It is not merely a producer of weirdness, it is a guardian of ordinary structure. It is one of the reasons reality remains usable from moment to moment. That usability is easy to underestimate because it is so constant. The bed supports you. The floor supports the bed. The walls stay outside the body rather than drifting politely inward. The cup contains the tea. The spoon stays spoon-shaped. The air moves through the room without the room dissolving into it. Your hands keep their shape while holding things. Your bones support your muscles. Your muscles move your bones. Your skin forms a boundary between your inner chemistry and the wider world. All of this depends on matter being stable, structured, and resistant in the right ways. Most of the time, you do not think of any of this as remarkable, you just live inside it. But physics allows you to notice the hidden conditions that make ordinary life possible, and once noticed, they are difficult to forget in the best possible way. It also changes the way one sees the phrase solid matter. That phrase sounds old and obvious until you know what it really hides. Matter is not solid because it is packed like ancient stone all the way down. Matter is solid because particles are arranged according to rules that create extension and resistance. When your hand meets a table, what you feel is not the final collision of tiny pebbles. You feel the result of electromagnetic interaction and quantum exclusion translated into pressure by your nervous system. When a wall stops you, it is not simply because it is made of hard bits. It is because the matter of the wall and the matter of your body cannot be compressed into the same arrangements without the world objecting very strongly. The world objects. It objects silently and consistently. And that objection is what ordinary life calls solidity. This is one of the reasons I find the principle so calming rather than merely strange. It explains not just the weirdness of the microscopic world, but the dependability of the human one. Deep down, reality is not a chaos barely pretending to be a room. It is a room because it is not chaos. It is a room because matter is constrained. The rules do not merely permit form, they insist on it. A chair is possible because atoms can settle into durable structures.
A wall is possible because those structures can occupy space in a way that excludes easy overlap. A body is possible because chemistry can become organized enough to maintain life. Beneath all the movement and uncertainty of daily existence, there is, at least in this respect, an extraordinary steadiness. Of course, the principle is not working alone. It never was. Electromagnetic interaction matters. Quantum mechanics as a broader framework matters. Nuclear structure matters. Chemistry matters. Biology matters. At each level, new kinds of explanation become useful. It would be foolish to turn the exclusion principle into a kind of mascot for all reality and let it take credit for things done by an entire team of physical laws. But it would be equally foolish to miss how central its contribution is. Some laws make motion possible. Some laws govern attraction and repulsion. This one, in part, governs distinctness. It helps to retell matter that it may not all collapse into one undifferentiated condition. That is an enormous job. And perhaps distinctness is the deepest theme here. The world is full of separations that make life possible. The cup is not the hand is not the table is not the floor is not the air. Your body has an inside and an outside. Cells have membranes. Organs have tissues. Atoms have electron structures. Materials have surfaces. Stars have limits beyond which one kind of support fails and another may take over.
Everywhere there are boundaries. Some are hard, some are soft, some are changing all the time, but none of them are trivial. The exclusion principle is one of the hidden reasons boundaries can exist in a durable way. That also makes it one of the hidden reasons the world is navigable. You can walk across a room because the floor remains where it is, and your feet remain where they are. You can pick up a glass because the glass resists the hand just enough to be grasped. You can lie down because the mattress deforms under weight without ceasing to be itself. You can breathe because the molecules involved in respiration have exactly the structures they do. You can think because your nervous system is built from stable chemistry. You can sleep because the body can trust the surfaces around it. The world is not merely there. It is cooperatively there. It meets you with form. Even when the principle shows up in extreme settings, it still does this same kind of work. In a white dwarf, it helps support matter against gravity. In a neutron star, a related exclusion-based resistance survives under conditions so severe that ordinary language begins to sound flimsy. The scale becomes enormous, but the character of the rule remains recognizable. Matter resists being forced into forbidden sameness. Whether the setting is an atom, a tabletop, or the remnant of a dead star, the principle keeps insisting on structure. It keeps saying that not all possible compressions are allowed. It keeps turning no into a kind of support. That may be why the subject circles back so naturally to the ordinary room. Once you have followed the principle into stars, it becomes hard not to look again at the very near world with renewed respect. The wall beside you is no longer only an inconvenience for dramatic exits. It is a stable material boundary built from atomic order. The blanket is not only soft fabric, it is organized matter-holding shape while yielding comfort. The mug, the shelf, the lamp, the window frame, the pillow, the page, all of them become visible as successes. Not emotional successes, physical ones. They are successful arrangements of matter in a universe that allows structure because it does not allow everything. There is also a gentle philosophical lesson here, though again it is not vague or mystical. It is simply that reality at human scale is not separate from reality at smaller scales. The room is not one kind of truth and the atom another. They are layers of one truth. The reason you cannot walk through walls is not an everyday fact floating free from deeper explanation. It is the everyday face of deeper explanation. The same world that contains quantum states contains hallways and cupboards. The same law that organizes electrons helps organize furniture. The same principle that shapes atomic structure helps make the body capable of needing sleep. Physics does not replace the ordinary world. It reveals why the ordinary world is there to begin with. And there is comfort in that revelation because it makes the familiar more trustworthy, not less. Sometimes people worry that science drains the world of immediacy or charm. But this kind of understanding does the opposite. It adds depth without removing usefulness. A wall is still a wall, a bed is still a bed. A hand held in another hand is still warm and immediate. Nothing important is lost by knowing more. If anything, the world becomes more textured. It becomes harder to dismiss ordinary existence as plain. The plainness was only the effect of repetition. Underneath it sits a level of order that is both strange and extremely dependable. I think that is part of why the principle feels quiet in the right way. It does not ask to be admired every moment. It does not turn the room into a science exhibition whenever you sit down. It does its work invisibly. It lets the world feel normal. Most of the best laws of nature behave like that. They are not eager for applause. Gravity does not introduce itself every time you set a cup down. Electromagnetism does not give a speech when a light turns on. The exclusion principle does not announce its presence when the floor supports your feet. It simply continues, with perfect seriousness, to enforce a rule that allows matter to remain differentiated and extended. The silence of that service is part of its elegance, and yet once you know it is there, you can hear it in a way. Not literally, of course, but intellectually. You can hear it in the firmness of the tabletop. You can hear it in the way a key resists your fingers. You can hear it in the confidence of a stair beneath the foot, in the integrity of a ceramic bowl, in the shape of a rib cage, in the persistence of a window glass under the weather, in the very fact that your body occupies one place and the wall occupies another. It becomes part of the hidden soundness of things. There is a lovely economy in that. A single principle, stated in the language of quantum states, reaches outward until it becomes one of the reasons the world can host ordinary life. Not the only reason. Not the whole explanation, but one indispensable reason. It gives matter a kind of disciplined abundance. It prevents collapse into sameness, and thereby permits richness, extension, contact, resistance, chemistry, and structure. The world does not merely survive that rule, it blossoms because of it. So perhaps the simplest way to end is where we began, though now the beginning looks different. Why can you not walk through walls? Because walls are not mere appearances of solidity, they are structured matter. Because your body is also structured matter. Because the electrons in that matter obey a rule that does not let them all merge into the same arrangement. Because the world at its smallest scales refuses certain kinds of sameness, and from that refusal the larger world gains shape and strength. Because reality is built from constraints that make stable things possible. That may not be the answer a child first expects, and it may not make a wall feel any more negotiable when one is in a hurry. But it does make the existence of walls, and floors, and bodies, and stars, and all the other durable objects in the universe feel more earned. They are not just there by default. They are there because matter has a hidden discipline. The universe is not made of vague stuff that somehow became furniture. It is made of particles and fields governed by laws that allow the ordinary world to hold together. And that, I think, is a good place to let the mind soften. Not with a grand conclusion, but with a steady one. The room around you is being held in shape by rules deeper than sight. The body resting here is one more arrangement of the same matter, obeying the same quiet order. The wall remains a wall, the bed remains a bed, the air remains air. The stars above, however distant, are made of the same kind of lawful stuff. The same universe runs through all of it, and somewhere beneath the visible calm of things, the exclusion principle is still doing its patient work, keeping matter distinct, keeping form possible, keeping the world intact while the night goes on.